Geological catastrophes are powerful and destructive events that occur on Earth, leaving traces that can be seen even after millions of years. These catastrophes can take many forms, but they are all manifestations of natural processes that occur on the planet and play a crucial role in its evolution. For example, over billions of years of Earth's existence, its surface has undergone numerous changes due to tectonic processes, atmospheric influence, and internal activity. Time on the planet flows slowly, and each catastrophe is just a brief moment in the endless flow of geological history. Mountains rise, seas retreat, and new forms of life emerge as a result of these catastrophic changes. For instance, volcanic activity can create new islands, while the sites of devastating earthquakes eventually form fertile plains. These processes take thousands of years, but they create conditions for the emergence of new ecosystems and biosystems. Geological time can be likened to an incredibly long film, where catastrophes are memorable scenes that shape the narrative but do not determine it. Over millions of years, Earth has experienced numerous such scenes, each contributing something new to the planet's appearance. For example, when sea levels rise, they flood lowlands, leading to the formation of new marine ecosystems that are later inhabited by diverse marine life. As a result of one such event, significant coral reefs were formed, which continue to serve as homes for numerous species. It is important to note that these geological catastrophes do not merely destroy the existing, but also create new opportunities for life and biodiversity. In this context, it is worth mentioning that large-scale events, such as asteroid impacts, not only caused mass extinctions, but also paved the way for new forms of life that subsequently developed and evolved. As a result of such catastrophes, new rocks and minerals are formed, which become the basis for life in new conditions. For example, volcanic eruptions enrich soils with minerals, promoting the rapid growth of vegetation in the future. Considering that geological processes occur on a scale that is difficult to comprehend, it can be confidently stated that catastrophes are an integral part of the life cycle of Earth. Each layer of sedimentary rocks that we can observe today contains evidence of these catastrophic events. These are, in a sense, books that tell the story of the planet's life over millions of years. In essence, geological catastrophes are not just destructions, but catalysts of change that ultimately lead to the formation of new forms of life and landscapes. For example, the formation of new mountain systems involves not only destruction, but also the creation of new biomes that can thrive in conditions previously unsuitable for life. From a temporal perspective, even the most destructive events are just brief moments in the billions-year history of Earth. This allows us to view the planet as a living entity capable of self-recovery and transformation. The geological history of Earth is a story of contradictions, where destruction and creation go hand in hand, creating unique conditions for life. For example, the collision of the Pacific and North American plates resulted in the formation of the Grand Canyon, one of the most famous natural formations on the planet. Ultimately, geological catastrophes are not just events, but important stages in the history of Earth, shaping its appearance and the conditions for life. Earth has experienced numerous such catastrophes, and each has left its mark on its history. The process of Earth's formation began around 4.5 billion years ago from a gas dust cloud that emerged as a result of supernova explosions. This cloud consisted of dust and gas particles that slowly but surely began to coalesce under the influence of gravity. In the early stages of Earth's formation, this process resembled chaos, where small bodies collided with each other, merging into larger objects. Each such collision released a colossal amount of energy, causing incredible heat. Temperatures in the center of the forming molten sphere reached thousands of degrees Celsius, while the surrounding environment was filled with steam and molten metals. Gradually, in this primordial cosmic chaos, planetesimals, protoplanets, formed over millions of years, significantly increasing the mass of the future Earth. These collisions were not random. They occurred in conditions where each new object was attracted to its neighbor, adding to the total mass and creating additional conditions for further growth. As a result of such processes, approximately after 100 million years, the first Earth prototype emerged, surrounded by clouds of gas and dust, with its surface pockmarked by constant impacts. Each new impact added not only mass, but also structured the surface of the body, creating the first mountain ranges and oceanic basins. Meanwhile, due to radioactive decay, processes were occurring inside this prototype that led to the formation of the planet's core, which began to release heat. This heat, in turn, facilitated the melting of some materials, creating conditions for the formation of Earth's mantle and crust. This was a long and arduous process, where each step required millions of years. Finally, approximately 3 billion years after the start of formation, Earth acquired a more or less stable shape, and its temperature began to gradually decrease, creating conditions for the appearance of the first oceans. At this stage, thanks to this chaotic process, the formation of what we now call a planet capable of supporting life began. Many researchers, such as John Martin and his team, have studied these early stages of Earth's formation, using data from meteorites that have preserved traces of the conditions in which they formed. Meteorites falling on Earth serve as a kind of time capsule, preserving information about the cosmic processes that occurred during the early formation of planets. Each such meteorite is not just a rock, but a window into the past, allowing us to study how exactly such celestial bodies, like Earth, came into being. The formation of Earth's primary crust occurred more than 4 billion years ago, when the planet's molten surface slowly cooled to form a thin, solid shell. At that time, Earth was a giant sphere of molten rock, with surface temperatures exceeding 1,000 degrees Celsius. Over time, as the planet cooled, dense layers of magma began to solidify, forming the first crust. This process was uneven. Different parts of the surface cooled at different rates, creating fragile areas that could easily be disrupted by the planet's internal forces. Research indicates that during this period, frequent tectonic activity and volcanic activity occurred, leading to the formation of cracks and faults in the crust that continually tore and deformed it. Volcanic eruptions spewed hot gases and magma onto the surface, creating new formations and destroying old ones. Around 3 billion years ago, when the crust had cooled enough to no longer glow with heat, Earth gradually entered a period of darkness. At this time, the atmosphere was not stable and consisted mainly of toxic gases such as methane and ammonia, creating conditions far removed from today's. During this period, the first continents began to form on Earth's surface, but they were small and fragmented, and their composition was significantly different from today's. Paleontological research shows that during this stage of crust formation, important physical-chemical processes took place that later became the basis for the development of life. The crust was mostly composed of light minerals such as granite and basalt, which were the result of cooling and crystallization of magma. It is important to note that the first continents were not stable and could easily be eroded by water and wind over millions of years. Over millions of years, the crust continued to evolve, absorbing carbon dioxide and releasing oxygen, which contributed to the formation of a more stable atmosphere. Around 2 billion years ago, Earth's crust reached its current structure, but it was still subject to destructive effects of tectonic processes that continue to this day. The process of forming the primary crust was not only a geological phenomenon, but also a climatic one, resulting in changes in surface and atmospheric conditions. The first stage of crust formation took about 100 million years, and it was during this period that the foundations for the future development of the planet were laid. Approximately 450 million years ago, in the depths of the solar system, a cosmic ballet unfolded, heralding the formation of the Moon. Two colossal bodies, Proto-Earth and the planet Theia, slowly approached each other, like two stars in a dance, governed by the laws of gravity. The mass of Theia was about 10% of the mass of Proto-Earth. When they collided, this event was one of the most powerful in the history of our planet. The collision was so powerful that it created vast clouds of heated gas and dust, ejected into orbit. This interaction occurred approximately 100 million years after the formation of Proto-Earth, and its effects are still felt today. As a result of the collision, part of the material from Proto-Earth and Theia was ejected into space, forming a disk of debris that later condensed and became the Moon. This process took several tens of millions of years, and during this time, the Moon was in a close orbit, leading to its surface being subjected to intense meteorite bombardment. The scale of the material ejection was immense. Scientists estimate that around 33 trillion tons of matter were ejected into orbit. Gradually, under the influence of gravity, this material began to collect and form a satellite that became a permanent companion of Earth. The Moon, born from the debris, witnessed the first steps of Earth on its path to creating conditions for life. This process can be compared to the birth of a star, when gas and dust begin to attract each other, forming dense clouds that eventually transform into shining celestial bodies. This grand but graceful symphony of cosmic forces, taking place in the silent void, became the foundation for the creation of our satellite, which today influences the tides and the biorhythms of all living organisms on Earth. These events occurred at a distance of more than 100 million kilometers from us. But thanks to modern technologies such as telescopes and satellites, we can study their effects and understand how they shaped our world. There are numerous hypotheses about how this dynamics developed, and each of them opens new horizons in the study of our system. As a result of a catastrophic collision between a young Earth and a Mars-sized body, known as Theia, a cloud of gas and debris formed, consisting of molten rock and particles. This event occurred approximately 4.5 billion years ago. The resulting cloud orbited around Earth and gradually began to condense into larger formations. Over several million years, particles in orbit began to coalesce due to gravitational forces. Small debris collided and combined, forming larger bodies that continued to accumulate material. The process was uneven. Some particles were drawn to the center, while others were ejected into space during collisions. But eventually more stable forms emerged. At this stage, the Moon was far from becoming the satellite we know today. Its surface was scarred by craters and lava flows, and conditions were far from favorable. However, as it cooled and solidified over millions of years, the Moon began to take its current shape. Gradually, its surface became more stable, and wide marine lowlands like the Sea of Tranquility and the Sea of Rains formed. These marine formations, composed of basaltic lava, give us insight into the geological activity of the Moon in its early years. Approximately 1 billion years after its formation, the Moon became a faithful companion to Earth. Its gravitational field began to influence the tides of our planet's oceans. This effect is the result of the interaction between Earth and the Moon, which causes the water level in the oceans to oscillate rhythmically. The Moon also stabilized Earth's axis of rotation, significantly influencing the climate and conditions of life on the planet. Research shows that without the Moon, climate fluctuations would have been much more pronounced, which could have led to significant changes in Earth's ecosystems. Even now, observing the Moon, we can see its craters and surfaces that preserve billions of years of history. Just recently, in 2009, scientists discovered traces of water ice on the Moon, opening up new prospects for future research and possibly colonization. The Moon, formed in the chaos of a cosmic collision, is now not only an important part of our system, but also a key to understanding the processes that occurred in the early years of our planet. Within the Artemis program, NASA plans to return humans to the Moon by 2024, allowing us to explore its surface more deeply and understand its influence on Earth. Late heavy bombardment was an era when young Earth was subjected to endless impacts from meteoroids and comets, leaving deep scars on its surface. During this time, when the planet was just beginning to form, its atmosphere was filled with steam and gases, and the landscape was a chaos of volcanoes spewing lava and oceans forming from molten magma. Each collision with celestial bodies, often the size of small cities, resulted in the creation of new mountain ranges and basins, forming unique geological structures. The impacts varied in strength. Some were powerful enough to eject debris into space, while others left deep craters that later filled with water, forming primitive oceans. These oceans, in turn, became centers for the formation of the first chemical reactions necessary for the emergence of life. Each new impact not only destroyed existing landscapes, but also provided the basis for new ones. Mountains were formed, new minerals appeared, and conditions on the planet gradually became more stable. Over time, Earth became less vulnerable, but the traces of these catastrophes remained in its geological history, marking moments of significant change. For instance, processes like differentiation, resulting from heating due to impacts, led to the formation of the core and mantle, dividing layers that we can observe today. Data from the period of late heavy bombardment help scientists understand how the planet became what we know it to be. By studying how each impact altered not only the surface, but also the internal processes, ultimately creating conditions necessary for life. These changes occurred over millions of years, forming unique ecosystems and creating conditions for the future evolution of various species. Thus, each impact was not just a catastrophe, but a part of a complex process that led to the creation of our world, rich in diversity and life. Earth, subjected to these impacts, became more complex and multifaceted, and its history continues to be an important subject of study for scientists seeking to understand how these transformations occurred. There are theories suggesting that it was during this period that conditions for life could have emerged on Earth due to the diverse chemical reactions taking place in the oceans and under the influence of ultraviolet radiation. Each stage of these changes left its mark in the geological record, allowing scientists to analyze and reconstruct events from those distant times. For example, the analysis of rock and mineral samples using radiometric dating provides insights into the time and conditions in which they formed, as well as how impacts affected the composition of the atmosphere. Currently, researchers continue to discover new evidence from this era, using modern technologies to analyze data, opening new horizons in our understanding of this planet. The atmosphere of the ancient Earth, which emerged around 4.5 billion years ago, was far from suitable for life as we understand it today. Initially, it consisted mainly of heavy gases such as carbon dioxide, ammonia, methane, and water vapor, resulting in atmospheric pressure several times higher than modern levels. There was virtually no oxygen in this primary atmosphere, making it inhospitable to most contemporary organisms. Consequently, the sky had a reddish tint because it was dominated by particles of dust and gases that reflected sunlight, creating an effect reminiscent of a sunset. Electrical discharges caused by frequent thunderstorms traversed this sky, producing bright lightning flashes that could reach temperatures of over 30,000 degrees Celsius. Under these conditions, chemical reactions took place, forming the first molecules that preceded life. For instance, in the 20th century, scientists like Stanley Miller and Harold Urey conducted experiments with what they called primordial atmosphere that recreated conditions similar to those on ancient Earth, enabling them to synthesize amino acids from inorganic compounds. These experiments confirmed that organic molecules could form under conditions that we now consider hostile. Complex processes occurring in the primary atmosphere laid the foundation for the formation of more complex compounds, ultimately leading to the emergence of life. However, the atmosphere remained highly aggressive, with frequent volcanic eruptions and meteorite showers constantly posing a threat to any budding life. Nevertheless, it was precisely in this chaos that conditions were born that later became the basis for the evolution and diversity of life as we know it today. Scientific research shows that during the first 100 million years of Earth's existence, the atmosphere underwent significant changes, including the removal of carbon dioxide and the appearance of the first traces of oxygen, which altered the composition of the atmosphere and prepared the ground for further evolution. As a result of intense bombardment of Earth by comets and asteroids, which occurred during the first several 100 million years of its existence, the planet began to fill with primary oceans. These celestial bodies, consisting of ice and rocky materials, brought not only water, but also a multitude of chemical elements and minerals to Earth. The water formed as a result of the melting of ice had a murky color, ranging from grey-green to dark blue, due to the high content of suspended particles and minerals such as magnesium, calcium, and sodium. The formation of primary oceans took place approximately 3.5 billion years ago, when the water level reached significant depths, creating vast water masses that covered a large part of the planet's surface. The water of these oceans was rich in various chemical compounds such as methane, ammonia, hydrogen sulfide, and carbon dioxide, which created a unique chemical environment conducive to the formation of the first biochemical processes. Research shows that it was in such conditions that organic molecules necessary for life emerged, as evidenced by the findings of ancient fossilized remains and geological formations. For example, in samples of sedimentary rocks from South Africa, dated to around 3 billion years ago, scientists discovered traces of simple organisms that likely originated in these mineral-rich waters. Additionally, the high iron content in the water gave the oceans a distinctive color, indicating oxidation processes that occurred in the primitive atmosphere. These oceans served not only as the home for the first living beings, but also as the foundation for the further evolution of life on Earth. As the planet cooled and the climate stabilized, the chemical composition of the water continued to change, leading to the formation of new compounds and, ultimately, to the emergence of complex life forms. The primary oceans, rich in minerals and chemical substances, became a catalyst for biochemical reactions that later formed the basis for the emergence of the first cells, and consequently, all known life. According to estimates by scientists, the volume of the primary oceans could have reached several million cubic kilometers, underscoring their significance in the history of Earth. The Earth's crust consists of numerous mobile sections that slowly drift across the planet's surface, creating plate tectonics. This concept implies that Earth is not static, but a dynamic system where plate tectonic processes have been occurring over billions of years. Each crustal section, known as a lithospheric plate, moves at different speeds, sometimes reaching several centimeters per year, which is equivalent to the rate at which human nails grow. These movements occur due to convective flows in the Earth's mantle, where hot materials rise to the surface and cooled materials sink. Thus, the constant temperature and pressure conditions in the mantle create the conditions for plate movement. Over geological time, these slow but continuous movements lead to the formation of new mountain ranges, faults, and even oceans. For instance, the collision of plates results in the formation of high mountain ranges like the Himalayas, which continue to rise even today. Conversely, the separation of plates can create new oceanic floors, such as the Mid-Atlantic Ridge, the longest mountain range in the world, stretching over more than 30,000 kilometers. Furthermore, the interaction of plates can lead to earthquakes and volcanic eruptions, which are the result of accumulated stress in the Earth's crust. One of the most famous examples is the San Francisco earthquake in 1869, which occurred due to the displacement of tectonic plates causing devastating consequences. Therefore, plate tectonics not only shapes the Earth's topography, but also influences climate, ecosystems, and the distribution of resources on the planet. As plates move, they also interact with mantle flows, leading to the formation of magma and subsequent volcanic eruptions, such as in Iceland, where volcanoes continue to actively erupt lava due to the constant movement of underground plates. Ultimately, tectonic processes are the key to understanding both the geological history of Earth and the current natural phenomena occurring on its surface. It is estimated that over the last 3 billion years, the area of continents has changed by more than 80%, highlighting the dynamism of our planet. Subduction is a process in which one tectonic plate slowly descends beneath another, returning to the Earth's mantle. This process occurs at the boundaries of plates, where one plate, typically oceanic, slides beneath a lighter continental plate. As a result of this interaction, tension builds up over a long period. For example, in the subduction zone off the coast of Japan, the Philippine Sea oceanic plate descends beneath the Eurasian continental plate. Pressure accumulates in this area due to the constant movement of the plates, and this can continue for decades or even centuries. When the tension becomes too great, it suddenly releases a large amount of energy, causing earthquakes. In Japanese history, earthquakes like the 1933 Kansai earthquake were the result of this process. The most powerful earthquakes in the world often occur in subduction zones where plates collide, as confirmed by numerous scientific studies. For instance, the 1923 Tokyo earthquake, which claimed the lives of more than 100,000 people, was the result of subduction when the tension between the plates reached a critical point. Additionally, this process also triggers volcanic activity, as the descending plate melts in the mantle, creating magma that rises to the surface. Mount Fuji in Japan, known for its activity, is a result of the subduction of the Philippine plate. In the subduction process, temperatures can reach thousands of degrees, and under pressure, magma chambers form, which can eventually lead to eruptions. Such processes also occur in other parts of the world, such as the Andes, where the Nazca oceanic plate descends beneath the South American continental plate. This interaction leads to the formation of powerful volcanoes like Visca Chancha and Sangai, which are actively erupting. Subduction also forms deep-sea trenches, such as the Mariana Trench, which is the deepest point on Earth and was formed as a result of plate collisions. This process not only shapes geological structures, but also influences the climate and ecosystems of regions with active volcanic activity. Each year, thousands of earthquakes are registered in subduction zones, and their consequences can be catastrophic for the population and infrastructure. Volcanic activity can also cause tsunamis, which pose a significant threat to coastal areas. For example, the tsunami caused by an earthquake in the Pacific Ocean in 2004 claimed the lives of more than 200,000 people in the Indian Ocean. Subduction is a crucial but dangerous process that shapes our planet and affects the lives of billions of people. During the process of seafloor spreading, magma rises from the Earth's depths through cracks in the ocean floor, creating new crust. This process begins at the boundaries of tectonic plates where they are moving apart. For instance, in the Mid-Atlantic Ridge, which stretches over 8,000 kilometers, magma from the mantle emerges to the surface, forming underwater volcanoes. The temperature of the magma can reach over 1,200 degrees Celsius. When magma reaches the ocean floor, it cools rapidly, forming new basaltic crust that gradually pushes apart neighboring sections of the floor. This process is the foundation for the formation of new oceans and the expansion of existing ones. For example, over the past 80 million years, the Atlantic Ocean has expanded by around 12,000 kilometers, thanks to seafloor spreading. Each year, up to several centimeters of new crust forms on the ocean floor, equivalent to the formation of a new land area that could eventually rise to the surface. Underwater volcanoes, such as Snake River Volcano, are clear examples of this activity. They can grow to heights of over 1,000 meters, with their cones always covered in a layer of fresh basaltic lava. These volcanoes not only create new land, but also influence the ecosystems around them, providing habitats for unique marine life. In places like the hydrothermal vents, where hot water and minerals are expelled from the Earth's interior, entire ecosystems based on chemosynthetic bacteria can form. Thus, underwater volcanism is not only a process of crust formation, but also the basis for life in the oceans. Seafloor spreading also affects the movement of continents, slowly pushing them apart. For example, over the last 100 million years, continents have shifted by distances exceeding 3,000 kilometers. This process is continuous and occurs over millions of years, making it one of the key factors in the transformation of our planet's appearance. Supercontinents represent vast land masses that form as a result of tectonic activity, when continents merge into a single entity. This process of union and disintegration occurs cyclically, and historically, it has been observed over hundreds of millions of years. For instance, according to geological data, over the past 200 million years, several supercontinents have existed, each leaving its mark on Earth's geological history. The most significant impact of supercontinents is on climate change. When all lands are connected, they form extensive internal continents where the climate becomes more continental, with more pronounced temperature fluctuations. Within such gigantic continents, precipitation is distributed unevenly, leading to the formation of deserts and arid regions. Conversely, when continents drift apart, oceans fill the gaps created, generating new ocean currents that, in turn, alter the climate conditions on the planet. For example, ocean currents like the Gulf Stream play a critical role in distributing heat across Earth's surface. The influence of supercontinents is also felt in the evolution of living organisms. Periods of land union create conditions for the migration and mixing of species, contributing to biological diversity. However, when land breaks apart, isolated ecosystems form on different continents, which can lead to evolutionary changes and the emergence of new species. For instance, isolation can result in the creation of unique ecosystems, such as the flora and fauna of Australia, which have developed separately from the rest of the world over millions of years. During the disintegration of supercontinents, new oceans also form, creating barriers between species, which in turn affects their adaptation and survival. Studying these processes helps us understand how tectonic movements influence the biosphere and shape ecosystems. From a geological perspective, Each supercontinent leaves behind unique geological formations, such as mountain ranges and rifts, which serve as witnesses to our planet's thousand-year history. For example, formations like the Appalachians in North America are remnants of ancient mountains formed as a result of continental collisions. Considering all these aspects, it can be said that the cycles of formation and destruction of supercontinents continually reshape the face of Earth and its climate conditions. Approximately every 200 million years, we observe a process where land again unites, creating a new supercontinent that will gradually disintegrate. As a result, our world is in a constant state of motion, with each new cycle leaving its mark on the planet's history. Pangaea was a supercontinent that existed approximately 300 million years ago and began to break apart around 200 million years ago. It had a unique shape, resembling a giant shovel stretched from north to south, and occupied almost the entire surface of the Earth, surrounded by a single ocean called Pannotia. In the center of Pangaea lay a vast territory that was predominantly arid, with deserts where temperatures could reach 40 degrees Celsius. Meanwhile, the coasts of Pangaea were influenced by monsoons, leading to seasonal rains and increased humidity in these areas. However, due to the continent's enormous size, most of its interior remained beyond the reach of marine winds, creating harsh climatic conditions. A moderate climate was virtually absent because Pangaea lacked sufficient mountain ranges to create local climatic zones, as is the case with modern continents. Consequently, the ecosystems that developed on Pangaea were limited, and the diversity of flora and fauna was not as great as it is today. Approximately 70% of the landmass was in tropical and subtropical climates, with dense forests and diverse plants along the edges, while the interior regions experienced water scarcity and various ecological stresses. The existence of Pangaea also contributed to the formation of massive mountain systems such as the Appalachians and the Urals, which arose from the collision of tectonic plates. These mountains formed barriers that influenced the climate but could not change the dominance of the arid center. Ultimately, the breakup of Pangaea into smaller continents such as Gondwana and Laurasia initiated the modern distribution of climatic zones and ecosystems. This process laid the foundation for the formation of the modern continents we know today and their diverse climatic conditions that have evolved over thousands of years due to tectonic activity. As a result, Pangaea became a pivotal stage in the geological history of Earth, determining not only its physical form, but also the climatic conditions that shaped life on the planet. The process of the breakup of Pangaea began approximately 200 million years ago, at the beginning of the Jurassic period, when the single continent slowly tore apart under the influence of tectonic forces acting on the Earth's mantle. Over the course of tens of millions of years, continents began to slowly drift apart, forming new oceans and seas. Initially, narrow seas, such as the Tethys, emerged between the parts of Pangaea, which later expanded and deepened. To understand this process, it is important to note that the movements of the Earth's crust occurred at a speed of only a few centimeters per year, which, on a geological timescale, appears as barely noticeable movement. But over the course of millions of years, it led to significant changes in the planet's geography. One of the first stages of the breakup was the formation of the ocean that is now known as the Atlantic. It began to form when the northeastern part of the continent separated from the southwestern part, and a rift gradually filled with water. As the further splitting of Pangaea continued over millions of years, continents such as Laurasia and Gondwana began to move in different directions, breaking up into smaller parts. For example, Gondwana, which included modern-day Africa, South America, Australia, Antarctica, and India, began to fragment into separate continents, also contributing to the formation of new oceans. Approximately 100 million years ago, during the Cretaceous period, the outlines of the modern continents were already well defined, and the Atlantic Ocean had significantly increased in size, reaching a width of around 3,000 kilometers at its widest point. At this time, the formation of the Indian Ocean began when India separated from Africa and began a slow movement to the north, which ultimately led to its collision with the Eurasian continent and the formation of the Himalayas. The process of the breakup of Pangaea not only represents the dynamics of tectonic plates, but also long-term climatic changes, as the change in the location of land and oceans affected atmospheric and oceanic currents. This, in turn, influenced ecosystems and biological diversity, which emerged as a result of the adaptation of organisms to new conditions. By the end of the Cretaceous period, around 65 million years ago, Pangaea had completely broken apart, and its fragments had taken on their modern forms, leading to the emergence of new seas and oceans, such as the Caribbean Sea and the Southern Ocean, which became important for marine life and ecosystems. As a result of these processes, which spanned millions of years, the world as we know it today is the result of a complex interaction of geological forces and the evolution of living organisms. The Atlantic Ocean began to form approximately 100 million years ago as a result of the breakup of the supercontinent Pangaea. During this period, a narrow strait between Africa and America gradually widened, creating conditions for the formation of a new ocean. Around 80 million years ago, during the Cretaceous period, active tectonic plate separation began, leading to the formation of the Mid-Atlantic Ridge, which became the main boundary between the North American and Eurasian plates on one side and the South American and African plates on the other. This ridge not only defined the ocean's boundaries, but also began to influence oceanic currents. For example, the Gulf Stream, which originates from warm waters near the equator, became more pronounced as the ocean expanded, transporting warm water northward and influencing the climate of North America and Western Europe. On average, the water temperature in the Gulf Stream reaches 24 degrees Celsius, which is significantly higher than in surrounding waters. As the ocean expanded, oceanic currents also changed, forming new routes that affected ecosystems. This period also coincided with changes in climate, with temperature and precipitation levels fluctuating on the continents, which in turn affected the evolution of terrestrial and marine organisms. For instance, increased currents facilitated the spread of nutrients, leading to a rapid growth of phytoplankton, the primary food source for many marine animals. Meanwhile, the Gulf Stream carried heat, while cold currents like the Labrador Current contributed to the cooling of coastal waters, creating conditions for the diversity of marine life. Around 65 million years ago, when the ocean reached its current size, its impact on climate became more pronounced. In particular, the formation of new marine routes facilitated the migration of various fish and marine mammals, such as whales and dolphins, which began to adapt to new conditions. As a result, the marine ecosystem began to diversify, and new species such as sharks and sea turtles emerged, adapting to various climatic zones. This demonstrates that the expansion of the Atlantic Ocean not only altered the geographical map, but also had a significant impact on the biological diversity of the region. Volcanism is a phenomenon where the internal energy of the Earth finds an outlet through fractures in the crust, ejecting molten rocks, known as magma, onto the surface. This magma is formed in the mantle, where temperatures can reach thousands of degrees Celsius and pressures become immense. Due to continuous convection processes in the mantle, molten minerals rise to the surface, creating a powerful tension between the internal forces of the planet and the crust that holds them back. This tension can accumulate over long periods until it finds release in the form of eruptions, when magma breaks through cracks and fractures. Notably, in some cases, the pressure can be so great that the crust begins to deform, forming underground reservoirs of magma that can cover areas of several hundred square kilometers. Volcanic activity is not limited to eruptions. It also includes processes such as gas emission, the formation of new mountain formations, and changes to the landscape. After an eruption, when magma reaches the surface, it quickly cools, forming various types of volcanic rocks such as basalt and andesite. These rocks can serve as the foundation for new ecosystems, creating unique conditions for flora and fauna. Volcanism also plays a significant role in shaping the climate, as the release of ash and gas can temporarily alter atmospheric conditions, as demonstrated by the massive eruption of Krakatoa in 1883, which caused a global drop in temperature. The study of volcanism helps scientists understand not only the processes occurring within the Earth, but also how these processes influence life on the surface. For example, the volcanism on the Hawaiian Islands, where hotspots in the mantle create new islands and also affect the ecosystems that adapt to constantly changing conditions. According to the US Geological Survey, around 30 active volcanoes erupt each year, highlighting the constant activity of these natural phenomena. Volcanism is not just a destructive force. It is a complex and multifaceted process that has shaped the Earth and its ecosystems over millions of years. Trapped volcanic activity is one of the most impressive processes on Earth, characterized by large-scale outpourings of basaltic lava that can cover vast territories. The most well-known examples of trapped volcanic activity can be found on the Deccan Plateau in India, where around 60 million years ago, powerful eruptions occurred, resulting in lava layers up to 2 kilometers thick. These eruptions took place over millions of years and eventually covered an area of about 1 million square kilometers. The lava flows slowly across the surface, forming wide and flat layers that gradually increase in thickness. Due to the low viscosity of basaltic lava, it can spread over large distances, sometimes reaching hundreds of kilometers from the eruption site. As a result, stepped plateaus are formed, which can have multiple levels, each corresponding to a specific eruption period. An example of such a plateau is the Columbia Plateau in the United States, where lava layers resulting from trapped volcanic activity reach a total thickness of more than 3 kilometers. These plateaus not only alter the landscape, but also significantly impact the climate and ecosystems of the region. During eruptions, not only lava flows are formed, but also mounds that can block rivers, creating new water bodies and altering hydrological systems. These processes also lead to changes in soil composition, contributing to the creation of unique ecosystems adapted to specific conditions. For instance, on the Deccan Plateau, fertile soils were formed, which later became the basis for agriculture in this region. These soils support a diverse range of flora and fauna, making them particularly valuable for biodiversity. It is important to note that trapped volcanic activity is not limited to India and the United States. Similar formations can be found in Iceland, where powerful eruptions occurred over thousands of years, creating picturesque landscapes and enriching the region's nature. The Orkney Islands, located off the northern coast of Scotland, also bear traces of trapped volcanic activity dating back to around 60 million years ago. Volcanic activity in these areas has left traces that we can still observe today in the form of characteristic geological formations. The processes associated with trapped volcanic activity have long-term consequences for the formation of the Earth's crust and the creation of new ecosystems that continue to develop even millions of years after the eruptions have ceased. The Siberian traps represent enormous volcanic formations that emerged approximately 250 million years ago at the end of the Triassic period and cover an area of about 1 million square kilometers. This makes the Siberian traps one of the largest volcanic provinces on the planet. Eruptions that occurred over the course of 1 million years created massive layers of basaltic lava, which in some areas reach a thickness of up to 2 kilometers. The volcanism was so intense that it ejected enormous volumes of ash and gases into the atmosphere, significantly altering the Earth's climate. As a result of these catastrophic events, the planet's temperature dropped, leading to what is known as the volcanic winter. Vast clouds of volcanic ash blocked out sunlight, creating a gloomy picture where day turned into night and the world was plunged into semi-darkness. Research indicates that the concentration of carbon dioxide and sulfur in the atmosphere increased significantly, leading to acid rain clouds and a sharp drop in temperature over several decades. Scientists such as Dr. Jonathan Castro from the University of California have calculated that the temperature drop could have reached 10 degrees Celsius, which in turn had a devastating impact on the ecosystems of the time. Massive eruptions could also have led to the extinction of many species, including dinosaurs, as the change in climate created unfavorable conditions for life. The Siberian traps not only affected local flora and fauna, but also altered planetary climate conditions, as evidenced by geological samples extracted from deep wells in Siberia and other regions. These findings indicate that volcanic activity in Siberia was linked to global changes in the biosphere and atmosphere, creating conditions that later contributed to the evolution of new forms of life. Volcanic eruptions also resulted in the formation of extensive deposits of valuable minerals such as nickel and copper, which continue to play a significant role in Russia's economy. The influence of the Siberian traps on planetary climate and ecosystems is still felt today, as they remain a subject of study for scientists seeking to understand how volcanism affects climate change and biological evolution. The Siberian traps, as colossal monuments of ancient catastrophes, continue to tell their story through geological layers that preserve evidence of the power of nature and its impact on life on Earth. Siberian traps played a decisive role in the Permian extinction, which occurred approximately 300 million years ago. This extinction is considered the most catastrophic event in Earth's history, when around 95% of all living species disappeared. The volcanic activity of the Siberian traps led to the release of enormous volumes of carbon dioxide and other greenhouse gases into the atmosphere. Carbon dioxide, accumulating in the atmosphere, contributed to global warming, which in turn caused significant climate changes. Studies show that the planet's temperature rose by several degrees, creating conditions for mass extinction of organisms. Scientists such as Dr. Jeffrey Kringensen from Arizona University point out that changes in temperature and atmospheric composition prevented ecosystems from adapting to the new conditions. Ocean acidification became another serious problem. Oceans, absorbing carbon dioxide, began to lose their alkalinity, which led to deterioration of conditions for marine organisms such as corals and mollusks, which could not survive in such conditions. According to research, the pH of oceans decreased by more than 0.3 units, having a catastrophic impact on marine flora and fauna. As a result of this process, known as ocean acidification, many marine ecosystems began to collapse. This was not just the extinction of individual species, but a mass extinction that affected entire groups of organisms, including fish and marine mammals. According to research published in the journal Nature, changes in ecosystems led to the collapse of food chains. Since small organisms such as plankton became unsuitable for survival, this affected larger predators that depended on them as a food source. The decrease in biodiversity and the destruction of ecosystems continued for millions of years, and this period is known as the Great Dying. Volcanic activity not only altered the atmosphere, but also led to the formation of toxic deposits that polluted soils and water bodies. There are data indicating that as a result of volcanic activity, a large number of toxic substances, such as sulfuric gas, were released. This led to acid rain, which destroyed vegetation and worsened living conditions on Earth. Climate and ecosystem changes caused by eruptions led to the planet acquiring a form incompatible with life. Massive changes in nature and climate affected even such resilient organisms as ancient plants and trees. Thus, the Siberian traps did not just leave a mark on geological history, but also served as a catalyst for one of the greatest extinctions that Earth has ever known. Scientists continue to study these processes to understand how volcanic activity can influence future climate changes. There are even hypotheses that such events could occur again if volcanic activity increases. Carbon dioxide emitted by volcanoes could again cause global warming, and this is no longer just a hypothesis, but a real threat to existing ecosystems. The Permian extinction serves as an important lesson about how volcanic activity can radically change not only the climate, but also life on the planet. Volcanic gases released into the atmosphere during eruptions can cause catastrophic changes that affect the entire biosphere. Mass extinctions are catastrophic events that periodically occur on Earth and lead to the disappearance of a significant number of species over a relatively short period. These phenomena are typically caused by a combination of factors, including climate change, volcanic activity, meteorite impacts, and even human activity. For example, at the end of the Permian period, approximately 250 million years ago, one of the most extensive mass extinctions occurred when around 90% of all marine species and 75% of terrestrial species disappeared. Such events can have profound consequences for ecosystems, creating voids that take millions of years to fill. Each extinction opens new niches for the survival and evolution of the remaining species, thereby forming new biodiversity. It is important to note that mass extinctions are not rare exceptions in the history of our planet. They have occurred at least 5 times, and each of these events was associated with global environmental changes. For example, at the end of the Triassic period, around 200 million years ago, an extinction event occurred that paved the way for dinosaurs to become the dominant terrestrial animals for the following period. Despite the fact that life always recovered after mass extinctions, the process was long and complex, requiring millions of years to restore biodiversity. Moreover, many species that disappeared never returned, highlighting the fragility of ecosystems. Recovery after mass extinctions is not only about the adaptation of the remaining species, but also about the possibility of new forms of life emerging to occupy the newly available ecological niches. This underscores how fragile and changeable life on Earth is. For example, after the extinction of dinosaurs at the end of the Cretaceous period, around 60 million years ago, mammals began to actively develop and occupy diverse ecosystems, ultimately leading to the emergence of humans. However, we are currently on the brink of a new mass extinction caused by human activities such as deforestation, pollution, and climate change. Scientists assert that the rate of species extinction is currently many times higher than the natural rate, and if no action is taken, the consequences will be catastrophic. For instance, according to the International Union for Conservation of Nature, more than 1 million species are at risk of extinction, which raises questions about the future of biodiversity on the planet. It is crucial to understand that each extinction leaves its mark not only on the history of Earth, but also on the development of all forms of life. For example, the disappearance of large mammals such as mammoths altered ecosystems and affected the climate, as these animals played a vital role in maintaining vegetation and soil. Considering the scale of previous mass extinctions, it can be concluded that life on Earth, despite its complexity and diversity, has always been subject to catastrophic changes. And each new challenge requires us to recognize the fragility of the existing ecosystems. Mass extinctions serve as a reminder of how quickly the world we live in can change and how important it is to care for our environment. Currently, scientists continue to study the causes and consequences of these events to better understand how to prevent future species losses and preserve existing biodiversity. The Permian extinction, which occurred approximately 250 million years ago, is considered the most significant mass extinction event known on Earth. 96% of marine and 70% of terrestrial species disappeared, leading to catastrophic consequences for the ecosystems of the time. In the oceans, where diverse marine life, including trilobites and ammonites, thrived, a slow decline in life began. Research indicates that over several million years, inhabitants of the deep sea faced increasing pressure from unfavorable conditions, such as changes in water temperature and oxygen levels. Scientists, including Dr. Richard Hyman, point out that during this period, there was a sharp increase in carbon dioxide in the atmosphere, which contributed to ocean acidification and the demise of coral reefs, which were a crucial component of marine ecosystems. On land, dramatic changes were also observed. Forests filled with tree ferns gradually disappeared, giving way to barren landscapes and lifeless terrains. Important groups of organisms, such as amphibians and reptiles, were also threatened with extinction. Archaeologist Dr. David Buddha's research shows that by the end of the Permian period, various ecosystems were unable to adapt to changing climatic conditions and new competitors that emerged. As a result, once rich ecosystems became desolate areas where survival became nearly impossible. Scientific data indicate that in some regions of the Earth, the level of biodiversity dropped to critically low levels, and entire groups of organisms, such as trilobites and some species of gastropods, disappeared forever. These events acted as a catalyst for evolutionary changes that ultimately led to the dominance of dinosaurs in the Mesozoic era. The Permian extinction served as a pivotal point in the history of life on Earth, demonstrating how fragile ecosystems can be in the face of rapid environmental changes. Scientific research on this topic continues, and each new finding helps us better understand the mechanisms that led to such a massive extinction of species. Notably, this event occurred over a relatively short period, just a few million years, making it one of the most catastrophic events in the planet's history. After the Permian extinction event, which occurred approximately 250 million years ago, Earth found itself in a state of severe ecological crisis. This event wiped out around 90% of all life forms on the planet, making it the most extensive mass extinction in history. The abandoned ecosystems became symbols of a new reality. The surviving species found themselves in conditions where competition was significantly reduced. Food chains simplified, and instead of complex ecosystems where diverse species coexisted, simpler structures emerged, dominated by a few groups of organisms. For example, in marine ecosystems, marine reptiles and some fish became the primary survivors, while on land, archosaurs, the ancestors of modern crocodiles and birds, took over. This dominance of the surviving groups created a unique atmosphere of rebooting evolution. The freed-up ecological niches allowed new forms of life to occupy these positions. Over the next several million years, new species began to appear, adapting to the changed conditions. In particular, the first mammals, although small in size, were able to adapt to various habitats, including forests and deserts. During this time, new groups of plants, such as gymnosperms, began to develop, diversifying the plant world that had previously been dominated by ferns. This was a period when life on Earth was rapidly changing. Plants that could survive in conditions of increased heat and dryness occupied ecosystems left by the extinction of previous species. Thus, in this complex and contradictory period, as Earth tried to recover from the catastrophe, innovative forms of life began to appear and actively develop, some of which became the basis for future ecosystems. This time laid the foundation for the formation of new biomes, which, over millions of years, became the habitats of modern animal and plant species. Fossils show that by the Triassic period, which began approximately 240 million years ago, ecosystems had become much more diverse than in previous epochs. In this time, archosaurs began to evolve into various forms, including dinosaurs, which later became the dominant land animals on Earth. Thus, the transitional period after the Permian extinction served as a catalyst for evolutionary changes that led to the appearance of new species and ecosystems, forming the basis for future biodiversity. Impact events refer to collisions between Earth and large celestial bodies, such as asteroids and comets, which have occurred throughout the planet's history. These catastrophic events can instantaneously alter conditions on Earth, leading to global catastrophes. For example, a collision with a body just a few kilometers in size can release energy equivalent to millions of atomic bombs, resulting in widespread destruction and changes to the climate and ecosystems. Shockwaves can trigger earthquakes, tsunamis, and wildfires across the planet, instantly killing millions of living beings and destroying ecosystems. There are signs that such events have led to mass extinctions, such as the Permian extinction, when approximately 90% of all species on Earth disappeared. Collisions not only destroy existing life forms, but also create conditions for the emergence of new species, altering evolutionary trajectories over millions of years. The fragility of planetary equilibrium becomes particularly evident when cosmic forces capable of erasing all life from Earth in a matter of hours come into play. Recovery from such catastrophes can take decades, and sometimes even millions of years, and even then, ecosystems can be radically altered. For instance, after a collision that occurred around 66 million years ago, which triggered the extinction of dinosaurs, Earth became a desert, and many species were unable to adapt to the new conditions. Scientists like Luis Alvarez proposed the theory that changes in climate and the disappearance of dinosaurs were consequences of such impact events. Scientific data shows that such collisions occur much more frequently than we think, and every 100 million years, we can expect a powerful impact that could reshape the planet. Around 160,000 years ago, a collision left traces on the ocean floor, causing massive waves and changes in geography. Some researchers claim that the probability of a collision with a large asteroid is 1 in 100 over the next century, highlighting the need for monitoring celestial objects and developing plans for Earth's protection. Even smaller events compared to global catastrophes, such as meteors a few meters in size, can cause local destruction and climate effects, making our planet vulnerable to external threats. Collisions with celestial bodies demonstrate that our life on Earth depends on many factors, and despite the apparent stability, we are constantly on the brink of danger. Impact events remind us that the planet can be subject to sudden changes, adding an element of unpredictability to our understanding of Earth's history. When a celestial body, such as an asteroid or meteorite, enters Earth's atmosphere, it encounters immense air resistance. At speeds of around 15 kilometers per second, the air in front of it compresses and heats up to temperatures of several thousand degrees Celsius, resulting in the formation of a luminous trail. This process is known as atmospheric braking. Upon impact with Earth's surface, the body releases colossal energy, equivalent to the explosion of several megatons of TNT, depending on the size and speed of the object. For example, a meteorite 20 meters in diameter can create a crater approximately 30 meters in diameter and up to 10 meters deep. The shock wave generated by the impact spreads through the atmosphere at the speed of sound, causing powerful seismic vibrations that can be felt hundreds of kilometers away. This results in the formation of a crater with a central uplift, where molten material is ejected outward, creating a characteristic bowl-like shape. The process of crater formation involves several stages. First, compression, then rupture, and the ejection of molten rock that can rise to heights of several kilometers. Seismic waves generated by the impact penetrate Earth's crust, causing shaking and even earthquakes. For instance, in 1930, the effects of a meteorite impact were felt in Chicago, despite the meteorite being small and falling more than 100 kilometers away. Strong seismic waves can alter Earth's structure and cause secondary effects such as landslides and tsunamis if the impact occurs in the ocean. Therefore, the process of forming an impact crater is a complex mechanism involving physical laws that release incredible energies and reshape the planet's landscape. An impact crater typically has a funnel shape surrounded by a rim of ejected material, which can include fragments of the meteorite and molten rock. For example, the Chicxulub crater in Mexico, formed around 65 million years ago, has a diameter of approximately 130 kilometers and is considered the site of the mass extinction of dinosaurs. The Chicxulub crater is located on the Yucatan Peninsula in Mexico and formed approximately 65 million years ago as a result of a meteorite impact with a diameter of about 10 kilometers. Its diameter is around 130 kilometers and its depth reaches approximately 24 kilometers, making it one of the largest known craters on Earth. The energy released during the impact exceeded the combined power of all nuclear weapons ever created by humanity and caused catastrophic changes on the planet. This impact served as a catalyst for the mass extinction event that led to the disappearance of around 70% of all species, including dinosaurs, which had dominated Earth for over 160 million years. Interestingly, the crater was discovered in 1981 by a group of researchers, including geologist Alan Hildebrand, who noticed anomalies in the regional geological structure. The Chicxulub crater possesses a unique geological structure. Its rim consists of layers of limestone, clay, and sandstone that formed as a result of both the impact and subsequent geological processes. It is believed that the crater not only influenced the climate conditions on Earth, but also led to changes in ecosystems, creating new niches for the survival of the remaining species. Currently, the crater is being studied by scientists from around the world who are examining its structure and the impact's consequences to better understand the processes of evolution on Earth. The place where the catastrophe once occurred now appears quite peaceful, but beneath the vegetation lies evidence of its vibrant and destructive past. Research shows that vast amounts of molten material were ejected to the surface, which cooled to form unique minerals such as quartz and feldspar. Scientists have also found traces of vegetation that existed before the impact, allowing them to reconstruct the appearance of the ecosystems of that era. The Chicxulub crater has become not only a geological, but also a historical object, reminding us of how suddenly and catastrophically the conditions of life on the planet can change. An asteroid that collided with Earth approximately 66 million years ago had a diameter of about 10 kilometers and was moving at an incredible speed of around 20,000 kilometers per hour. This colossal speed resulted in an impact energy equivalent to approximately 130,000 megatons of TNT, which was 16 times greater than the total power of all nuclear warheads on the planet. At the moment of impact, a flash of light occurred, its brightness exceeding that of the sun several times. A cloud of dust and gas was formed, rising to tens of kilometers into the atmosphere. The shockwave caused powerful earthquakes that were felt thousands of kilometers from the impact site. As a result of this catastrophic event, there was an instantaneous vaporization of rock that formed the Chicxulub crater, with a diameter of around 130 kilometers and a depth of more than 20 kilometers. The resulting crater became not only a geological anomaly, but also a crucial element in the study of the consequences of such collisions. The explosion ejected a massive amount of debris and dust into the atmosphere, leading to a sharp change in climate, blocking sunlight and lowering the planet's temperature for several years. Some of these debris reached space, serving as a clear indication of the impact's force. This event is considered one of the main factors that led to the mass extinction of dinosaurs and other species, paving the way for the evolution of mammals. The Chicxulub crater became not only an object of geological research, but also a symbol of the power of nature, capable of changing the face of an entire planet in an instant. At the moment of Chicxulub's impact, several catastrophic events unfolded, transforming the planet's appearance in just a few hours. The first consequence was a massive firestorm that engulfed vast territories. Temperatures on the surface soared to such heights that wood and vegetation ignited, creating powerful fire tornadoes. Scientists estimate that at least a third of Earth's vegetation, including ancient forests that had existed for millions of years, was consumed. Then came a tsunami with a height of up to 100 meters, which devastated coastal areas. This force turned coastal zones into chaos, leveling everything in its path, from small settlements to large ecosystems like mangrove and coral reefs. At the same time, earthquakes, triggered by the shifting of the Earth's crust, shook continents, causing destruction in the habitats of dinosaurs and other species. They contributed to the formation of new cracks and fault lines, exacerbating the situation. Soon after these catastrophic events, acid rain began, caused by the release of sulfur and other toxic gases into the atmosphere. These rains eroded soil and poisoned water bodies, making survival impossible for many species. Research shows that the acidity in the rain exceeded levels capable of destroying life on the surface. Ecosystems that had existed for millions of years were on the brink of total annihilation. Meanwhile, many scientists assert that such conditions could have led to the extinction of up to 85% of all species on the planet. That day, when the familiar world crumbled into chaos, was a true apocalypse in Earth's history, leaving behind desolate landscapes and dead nature that took a long time to recover. Scientists like Dr. Larry Weiss from the University of California emphasized that the effects of this impact were felt for millions of years, shaping new biomes and ecological niches in conditions that were vastly different from before. The impact of Chicxulub, which occurred around 66 million years ago, led not only to the immediate destruction of life, but also to long-term climate changes known as the impact winter. The powerful collision with an asteroid released energy equivalent to millions of atomic bombs, sending tons of dust and debris into the atmosphere. This dust created a thick veil that blocked sunlight and plunged the planet into darkness for several months, and in some regions, even for years. Estimates suggest that the surface temperature of Earth could have dropped by 10 to 20 degrees Celsius, leading to a significant cooling of the oceans. Photosynthesis nearly ceased, and plants, upon which herbivores depended, began to die out. According to paleontologists, this led to the collapse of food chains, starting from the base, i.e., plants, and ending with top predators like dinosaurs. While some species disappeared, others, more resilient, attempted to adapt to the new conditions. But the scale of extinction left its mark on ecosystems. Scientists like Dr. Peter Ward from the University of Florida claimed that this impact winter was the catalyst for the mass extinction, resulting in the disappearance of more than 70% of all species. The world, shrouded in darkness, resembled a post-apocalyptic landscape. Dark clouds hovering over the Earth blocked the light, creating conditions where temperatures dropped to critical levels. In the oceans, a process known as dead zones began, where oxygen was depleted and life in the waters practically ceased. Coral reefs, which were home to numerous marine organisms, started to disintegrate as their symbiotic algae could not survive without light. This coral extinction further impoverished marine fauna, and ecosystems that had existed for millions of years began to crumble. According to research conducted by Dr. Emily Gray from the Scripps Institution of Oceanography, even after light began to return, ecosystems recovered slowly. Recovery took tens of millions of years, and new species that filled the vacated niches were entirely different from their predecessors. For example, new types of fish that adapted to the changed conditions appeared in the sea, but they had nothing in common with the dinosaurs that once dominated the planet. What happened was not just a catastrophe for the dinosaurs, but also the beginning of a new era for mammals, which eventually occupied the freed-up ecosystems. During this time, when life on Earth was recovering, temperature began to rise again, facilitating the emergence of new, more complex forms of life. This also led to a greater diversity of ecosystems, which in turn contributed to the emergence of mammals, one of which was our ancestor. The period of the impact winter and the subsequent recovery of ecosystems have become important topics of study in paleontology and climatology. Scientists continue to investigate how climate change affects life on Earth today, and how events like the Chicxulub impact can serve as a warning about the possible consequences of human activity. Each time we face climate challenges, we can look back at this historical moment and understand that Earth has already survived catastrophes of much greater magnitude. The Chicxulub impact, which occurred around 60 million years ago, was a catastrophic event that significantly affected the existence of dinosaurs, which had dominated Earth for over 150 million years. The impact of an asteroid, estimated to be 10 kilometers in diameter, caused immense destruction, creating a crater approximately 130 kilometers in diameter on the territory of the modern Yucatan Peninsula in Mexico. This impact triggered powerful earthquakes and tsunamis that flooded coastal areas and released billions of tons of dust and gas into the atmosphere, leading to a significant decrease in sunlight. Within a few days after the impact, the planet's temperature dropped sharply, resulting in a rapid change in climate and ecosystems. Dinosaurs, including species such as Tyrannosaurus rex and Triceratops, found themselves in conditions to which they were not adapted. These creatures were unable to quickly adapt to new conditions such as cooling, loss of vegetation, and changes in food chains. According to research conducted by paleontologists such as Dr. David Pohl, it was the sudden change in climatic conditions that led to the mass extinction of around 70% of all animal species on the planet. Massive extinctions occurred over several thousand years, not instantaneously, and as a result, there were no dinosaurs left that once dominated ecosystems from forests to deserts. Instead, mammals began to develop and occupy the niches left vacant by their disappearance. For example, small mammals, such as the ancestors of modern rodents, survived due to their ability to hide and adapt to various conditions, while dinosaurs like Zunopateor or Stegosaurus could not survive in the new conditions. The process of dinosaur extinction was not just the loss of certain species, but an entire era when great creatures that seemed invincible ruled the planet. As a result of this cataclysm, space was created for new forms of life, including mammals and birds, which began to evolve and develop in conditions where dinosaurs could no longer compete. An important aspect of this process is that the Chicxulub impact was not just a single event, but a turning point in the history of life on Earth. After more than 150 million years of dinosaur dominance, the planet entered a new era filled with new species and forms of life. The extinction of dinosaurs opened the door for mammals, which eventually led to the emergence of humans, who became the dominant species on the planet. While dinosaurs left behind only fossils and myths, new forms of life began their triumphant march across the Earth, continuing the evolution that had been interrupted by this catastrophic event. The Cretaceous-Paleogene extinction event, which occurred around 66 million years ago, affected ecosystems worldwide. But some groups of organisms not only survived, but also thrived in the new, altered world. Small mammals, such as the ancestors of modern rodents and insectivores, exhibited remarkable adaptability to the conditions following the catastrophe. Their small size allowed them to hide in burrows and shelters, avoiding predators and competition for resources. For instance, mice and rats, which were widespread at the time, were able to reproduce rapidly, filling the vacant niches. This gave them a significant advantage as they could adapt to various environmental conditions, including changes in diet and habitats. Birds that survived the extinction also found ways to adapt to the new environment. Some species, such as the ancient ancestors of modern passerines, began to develop lighter bones and improved flight abilities. Around 50 million years ago, birds capable of long-distance flights already inhabited Earth, allowing them to quickly move in search of food and shelter. Crocodiles, which survived the catastrophe due to their reptilian physiology, continued to live in water bodies and marshes, preserving their ecosystem. Their ability to survive in extreme conditions, such as high temperatures and low oxygen content, made them one of the few species that could maintain their populations. Turtles, with their hard shells and ability to endure long periods of fasting, also survived the catastrophe. They went into a state of torpor when resources were limited, allowing them to survive until more favorable conditions arrived. The radiation of these groups began in the Eocene, when the climate became more stable and diverse. Around 50 million years ago, in North America and Europe, new species of mammals, such as primitive ungulates and the ancestors of modern predators, began to appear. This era was a time of ecological flourishing, when mammals began to populate various ecosystems, from forests to grasslands. The total number of mammalian species increased from a few dozen to thousands, allowing them to occupy all available ecological niches and develop diversity in form, size, and lifestyle. During this time, new groups of birds also emerged, including birds of prey and owls, which filled the gaps in food chains. The adaptations that allowed these groups to survive became the foundation for their further evolutionary development and the formation of modern ecosystems. An example of this process is the group of mammals known as primates, which began to develop in forest ecosystems, ultimately leading to the emergence of humans. Supervolcanoes are massive geological structures capable of erupting on a scale significantly larger than ordinary volcanoes. These volcanoes are characterized by eruptions that can expel between 1,000 and hundreds of cubic kilometers of material, including ash, lava, and gas. Unlike typical volcanoes, supervolcanoes have enormous calderas that can reach tens of kilometers in diameter. A caldera forms after a colossal eruption, when the magma chamber beneath the volcano is emptied and the surface of the Earth collapses, leaving behind a vast depression. Supervolcanoes are formed over long periods of time as magma accumulates beneath the Earth's surface, leading to the buildup of immense pressure. When this pressure reaches a critical point, an eruption occurs with incredible force, expelling a vast amount of material into the atmosphere. The potential impact of such an eruption on global climate can be catastrophic. For instance, the release of volcanic gases such as sulfur dioxide can cause a sudden drop in global temperature, leading to short-term ice ages. Long-term consequences can include changes in ecosystems, mass extinctions of species, and economic catastrophes due to food shortages. Throughout Earth's history, events related to supervolcanoes have had significant impacts on climate and life on the planet, underscoring their importance and the need for studying such geological phenomena to understand their potential influence on humanity's future. The scale of supervolcanoes and their potential consequences make them unique objects of study in geology and ecology. It is important to note that supervolcanoes can remain dormant for thousands of years but may suddenly become active, making their study highly relevant. Supervolcanoes can not only erupt lava, but also massive amounts of ash that can cover large areas, making them extremely dangerous to human life and health. For example, such an eruption can lead to a so-called volcanic winter, where sunlight cannot reach the Earth's surface due to ash clouds, causing a sharp drop in temperature. These phenomena highlight the importance of monitoring potentially dangerous volcanoes to predict possible catastrophes in advance. Supervolcanoes are typically located in areas where tectonic plates collide or diverge, creating ideal conditions for magma accumulation and subsequent eruptions. Historical data on such eruptions can help scientists better understand how supervolcanoes affect climate, ecosystems, and human life. Yellowstone caldera is one of the largest and most active volcanic formations in the world, with a diameter of around 30 kilometers. It was formed as a result of 3 major eruptions, the last of which occurred approximately 600,000 years ago. This event released about 1,000 cubic kilometers of magma and rock, resulting in the formation of a vast depression. The structure of the caldera includes several layers of volcanic deposits that indicate multiple eruptions and changes in geological activity. Inside the caldera, there are hot springs and geysers, such as the famous Old Faithful geyser, which shoots water up to 45 meters every 90 minutes. These natural phenomena are just small manifestations of a vast magma reservoir hidden beneath the surface. Research shows that beneath the caldera lies a magma chamber with a volume of about 700 cubic kilometers, making Yellowstone one of the most powerful supervolcanoes on the planet. Geologists believe that an eruption of this supervolcano could have catastrophic consequences not only for the United States, but for the entire world, as the release of ash and gas could affect the climate, lead to temperature drops, and destroy agriculture over large areas. In recent decades, scientists have observed an increase in seismic activity in the caldera area, which may indicate the movement of magma. For example, in 2018, more than 30,000 earthquakes were recorded within Yellowstone National Park, significantly exceeding average levels. This creates a sense of hidden power, as beneath the picturesque landscape lies a giant force ready to manifest at any moment. Special research shows that the temperature in the magma reservoir reaches more than 1,000 degrees Celsius, underscoring the volcano's activity. The caldera is surrounded by mountains formed by volcanic activity, and these natural barriers create a unique ecological balance where flora and fauna have adapted to specific conditions. Geysers and hot springs, such as the Midway Geyser Basin with its vibrant, almost neon colors, are the result of high temperatures and minerals in the water. These characteristics make the area around the caldera a unique place for studying volcanic activity and the ecosystem that exists under constant geological stress. Scientists continue to study this remarkable natural phenomenon to better understand how it affects the climate and ecosystems as a whole. The last major eruption of the Yellowstone supervolcano occurred around 600,000 years ago and was one of the most powerful volcanic events in Earth's history. This eruption, known as the Yellowstone eruption, released approximately 1,000 cubic kilometers of ash and rock into the atmosphere, equivalent to the volume needed to fill more than 300,000 Olympic-sized swimming pools. The ash spread over thousands of kilometers, reaching distant regions such as the central parts of the United States and even the eastern coast of the country. As a result of this massive release, the sky over significant areas was obscured by a thick layer of volcanic ash, leading to a sharp decrease in sunlight reaching the Earth's surface. In some places, sunlight was reduced by more than 90%, causing catastrophic changes in climate. Temperatures in North America dropped by several degrees, making summer months significantly colder and winters more severe. This change in climate led to the extinction of many plant species that could not adapt to the new conditions. Vegetation withered under the layer of volcanic material, and ecosystems that had existed for thousands of years were threatened with extinction. Scientific research shows that this eruption could have caused what is known as a volcanic winter, where the planet's temperature dropped and agricultural yields declined sharply, potentially leading to famine and social upheaval. Even after such a long time, scientists continue to find traces of this catastrophic event by studying layers of sedimentary rocks that preserve information about volcanic activity. Ash found in places like Missouri and Tennessee testifies to the scale of the destruction that not only affected ecosystems, but also human communities living in North America at that time. Volcanic ash that settled on the ground contained minerals that influenced the soil in these regions, changing agricultural conditions for many decades to come. As a result of the aftermath of this eruption, ecosystems adapted to the new conditions, and new species replaced the extinct ones, forming the basis for the modern ecosystems in these regions. This phenomenon is still remembered by contemporary researchers who analyze the consequences that such catastrophic events can have for our planet. The volcanic activity in Yellowstone continues to attract the interest of scientists. The supervolcano Toba on Sumatra is one of the largest volcanoes on the planet. Its caldera was formed as a result of a colossal eruption that occurred approximately 78,000 years ago, when the volcano ejected more than 30 cubic kilometers of magma into the atmosphere, leading to significant climate changes. The Toba caldera is about 130 by 40 kilometers in size, making it one of the largest in the world. In the center of the caldera lies the magnificent Lake Toba, which is approximately 100 kilometers long and up to 25 kilometers wide. The depth of the lake exceeds 400 meters, making it the deepest lake in Indonesia. The water in Lake Toba has a bright blue color, and the surrounding mountains create a stunning contrast with the serene landscape. This natural oasis hides a destructive force that could awaken at any moment. The volcanic activity of Toba has been recorded approximately 7 times over the last 2 million years, and previous eruptions were significantly larger than modern volcanoes like Krakatoa. Scientists from various countries, including research conducted by a group of geologists from Harvard University, under the leadership of Professor Daniel Fink, continue to study the potential activity of the supervolcano. They analyze layers of sediments and minerals to assess possible scenarios for future eruptions. Local residents living on the shores of Lake Toba often do not suspect the hidden danger, as the landscape around them appears idyllic. However, beneath the waters of Toba lie giant magma reservoirs that could cause catastrophic events. Today, Toba is considered a dormant volcano, but its potential activity causes concern among geologists. Each year, research is conducted on Lake Toba, and its ecosystems and impact on the climate are studied. It is interesting to note that the volcano Toba, despite its destructive nature, has become an important tourist attraction. Thousands of tourists visit to enjoy the beauty of nature, explore local cultures, and learn about the geological history of this unique place. Lake Toba has also become a site for the study of ancient human settlements, as archaeologists find artifacts belonging to ancient civilizations that once inhabited these lands. In this context, Toba is not only a natural wonder, but also an important object for the study of the history of our planet, its climate changes, and their consequences for humanity. The volcano Toba continues to hold its secrets, and its study can shed light on many aspects related to volcanic activity and its impact on life on Earth. The eruption of the Toba volcano, which occurred approximately 74,000 years ago, is the most powerful known volcanic event in human history. This event resulted in a massive release of ash and gases into the atmosphere, leading to global climate changes. Scientists estimate that during the eruption, around 30 cubic kilometers of volcanic material were released. The ash obscured the sun, causing the sky to be darkened for several years. The Earth's temperature dropped sharply, leading to what is known as the volcanic winter effect. This cooling could have lasted from 5 to 10 years, depending on the region. Vegetation in extensive areas was affected, leading to food shortages. This catastrophic climate change had a devastating impact on early humanity, which at that time numbered only a few tens of thousands of individuals. Scientists estimate that the human population could have declined to a few thousand due to resource scarcity caused by environmental changes. The eruption of Toba resulted in a significant genetic bottleneck in human population history, which can be traced through DNA analysis of modern humans. Research shows that all modern humans share a common genetic code that emerged after this catastrophic event. Early Homo sapiens living in Africa faced unforeseen challenges, which may have prompted them to migrate to more favorable conditions, thereby altering the course of human history. The volcanic activity of Toba not only led to social and ecological consequences, but also to changes in human migration patterns, which became a significant factor in the formation of the modern human population. The Toba volcano not only left its mark on history, but also became an important object of study in the fields of climatology and anthropology. Studying the Toba eruption presents a unique opportunity to understand how catastrophic natural events can influence the development of humanity and its adaptation to changing conditions. The ash released into the atmosphere spread over thousands of kilometers, forming a thick layer on the surface that can still be detected today. Scientists from various countries, including Indonesia and the United States, continue to study the deposits to better understand the scale and consequences of this magnificent yet destructive event. The Toba volcano has become not only a subject of study for geologists, but also a symbol of the power of nature to shape the course of human history. Volcanic activity significantly influences the Earth's climate system, creating complex and multi-layered interactions between the planet's internal processes and atmospheric conditions. When volcanoes erupt, they release gases such as sulfur dioxide and carbon dioxide, which enter the upper layers of the atmosphere and can alter the transparency of the air. For example, sulfur dioxide in the atmosphere can convert into sulfuric acid, forming aerosols that act as tiny mirrors, reflecting sunlight back into space. This leads to a decrease in surface temperature as less solar energy reaches the Earth and oceans. Meanwhile, carbon dioxide, also released during eruptions, contributes to the greenhouse effect, trapping heat in the atmosphere and potentially contributing to long-term global warming. Volcanic ash, ejected into the atmosphere, can depend on the strength of the eruption and the composition of the lava. Larger eruptions can release millions of tons of ash that can remain in the atmosphere for several weeks to several years. This also affects the climate, as ash and aerosols can alter cloud cover and weather conditions, hindering precipitation and causing droughts in some regions. Studies conducted by meteorologists and climatologists show that even small changes in volcanic activity can have a noticeable impact on global climate conditions. For instance, the eruption of the Krakatoa volcano in Indonesia in 1883 caused a significant drop in global temperature, leading to unusually cold summer months in Europe and North America. Therefore, volcanic activity can both cool and warm the climate depending on the type and scale of the eruption, and the results of these processes can persist for decades. Comprehensive climate change models developed by scientists include data on volcanic activity, demonstrating that volcanoes play a crucial role in shaping climate patterns. These models help predict how future eruptions may affect the climate and show that Earth's internal processes are directly linked to atmospheric phenomena. Studying these interactions allows us to better understand how volcanic activity can alter the usual course of climate change and its consequences for ecosystems and human life. For example, the consequences of volcanic activity can manifest in changes in animal and plant migration patterns, as well as in changes in agricultural practices. Volcanic gas emissions can also affect human health, causing respiratory diseases, especially in nearby populated areas. Models that consider data on volcanic activity show that short-term and long-term climate changes can impact global food systems, highlighting the need for careful monitoring of volcanoes and their activity to predict and minimize risks. Volcanic activity and climate change are two sides of the same coin, where each process influences the other, creating a constant change in conditions on the planet. In this context, it is important to note that nature is not a static system, but a dynamic interaction of many factors, including volcanism, which, as practice shows, can have a significant impact on climate conditions over the course of millennia. In the year 1816, the world experienced one of the most peculiar and tragic years in its history, known as the Year Without a Summer. This anomalous phenomenon occurred due to the powerful eruption of the Tambora volcano on the Indonesian island of Sumbawa in April 1816, which released a massive amount of ash and sulfur into the atmosphere. The volcanic activity was so intense that for several years after the eruption, significant climate changes were observed worldwide. The summer of 1816 became a nightmare for the residents of Europe and North America. Temperatures below normal, heavy rainfall, and even snow in July became common occurrences. In places like New York and Connecticut, people woke up to snow-covered landscapes in the middle of summer, when they usually experienced heat waves. This summer was not only cold, but also gloomy. The ash clouds that enveloped the sky blocked out the sun and caused a perpetual twilight, adding to the atmosphere of unease. As a result, crop failure became commonplace. Farmers could not harvest enough food, leading to famine that affected large regions. In Europe, grain prices skyrocketed, causing concern and protests among peasants. In the United States, in some areas, crop yields fell to 30% of normal levels. Letters from the time described not only the cold, but also widespread despair, as families struggled to feed themselves. A notable event was the meeting of poets and writers in Geneva, where Byron and Shelley discussed the climate changes, drawing inspiration from the unusual weather phenomena for their works. This unprecedented situation gave rise to myths and theories that this was divine punishment for humanity's sins. People were confused and sought explanations in religion and superstitions, reflecting their fear of nature's unpredictability. Snow in July, frozen fields, and famine in homes became symbols of the complete disruption of the usual rhythm of life. This year served as a prologue to significant social and economic changes in society, and its consequences were felt for a long time. Estimates suggest that around 100,000 people died from hunger and diseases caused by food shortages. The unpredictable climate changes of 1816 left an indelible mark on people's memories and became a significant lesson about the interdependence between natural phenomena and human destinies. In response to this climate catastrophe, many countries began to seek ways to improve agriculture and strengthen food security, realizing that nature can be both a source of life and a cause of death. The year 1816 was memorable not only for its climatic catastrophes, but also for the cultural transformations that reflected human experiences and fears. During this time, when the sky was shrouded in grey clouds and the sun barely pierced the veil of ash, Mary Shelley, inspired by the gloomy atmosphere, wrote her famous novel, Frankenstein. Published in 1818, this work was not just a literary piece, but also a reflection of anxieties about the consequences of scientific progress and the rupture with nature. Mary Shelley, part of a circle of poets and writers that included figures like Byron and Percy Shelley, depicted in her novel the fears associated with human intervention in nature. The creature created by Victor Frankenstein symbolized not only the consequences of irresponsible scientific experimentation, but also the dark moods of the era when people became aware of their vulnerability in the face of natural forces. At the same time, artists used dark landscapes to convey a sense of hopelessness and apocalypse. For instance, the famous artist Joseph Mallord, William Turner, created works like The Burning of the Houses of Parliament, which depicted the fury of nature and human suffering. His paintings, filled with dark hues and turbulent emotions, became symbols of the time when nature appeared as a powerful enemy. Artists of the period sought to capture not only external changes, but also the internal experiences of people overwhelmed by fear and uncertainty. The sense of hopelessness and the search for meaning found expression in poetry. Romantic poets like Lord Byron addressed themes of solitude and inner struggle in their works, creating images that resonated with the society's moods. As a result, the art and literature of this era became reflections not only of climatic changes, but also of profound social and philosophical questions. The gloomy moods born of the Year Without a Summer inspired many creators, and their legacy continues to influence contemporary art and literature. In a time when nature became a symbol of death and destruction, human creativity in turn became a response to the challenges of the time, producing works that remain classics to this day. Within the framework of Romanticism, great literary and artistic works were created, serving as a kind of therapy for people seeking to understand and make sense of the world around them. During this period, when humanity faced a climatic catastrophe, it found in art a way to express its fears, hopes, and experiences, thereby enriching world culture. As history shows, even the darkest moments can be a source of inspiration and creativity. Glacial periods are complex climatic phenomena that have shaped the history of Earth over millions of years. Each glacial period is characterized by cyclicity, with glaciers gradually advancing to cover vast continental territories and then retreating, leaving behind altered landscapes. These cycles can last for tens of thousands of years, and their impact on the geography, flora, and fauna of the planet is immeasurable. During the maximum expansion of glaciers, the thickness of the ice could reach several kilometers, creating enormous pressures on the Earth's crust and leading to tectonic changes. For example, under the influence of this pressure, new forms of relief such as moraines, lakes, and deep valleys were formed. Glaciers moving at a speed of only a few centimeters per year slowly but surely altered the courses of rivers, creating new water bodies and changing ecosystems. In some places, this led to the formation of glacial lakes, such as Lake Michigan or Lake Tahoe, while in others, it resulted in the formation of vast plains. Glacial periods also affected sea level. During the maximum expansion of glaciers, sea level dropped by several hundred meters, opening new land bridges between continents. This allowed animals and humans to migrate, creating new routes and altering the dynamics of species distribution. The alternation of glacial periods was linked to changes in solar activity and variations in the Earth's orbit, as confirmed by studies conducted by scientists such as Milutin Milankovitch, who proposed the theory of orbital cycles affecting climate. These cycles, known as Milankovitch cycles, include changes in the eccentricity of the Earth's orbit, the inclination of its axis, and its precession. As a result of these changes, the climate could shift from cold to warm, which, in turn, influenced the glacial cycles. Thus, glaciers moving across continents not only created new physical forms, but also influenced climatic conditions, affecting the lives of all planet inhabitants. Glacial ridges and rocks left behind by retreating glaciers serve as important evidence of these changes, providing geologists and paleontologists with information about previous climatic conditions. Research shows that such glacial deposits can be found even on the equator, indicating the global nature of these processes and their significance for understanding the climatic history of Earth. About 20,000 years ago, during the last glacial maximum, Earth was in a state of deep glaciation, covering significant parts of the northern hemisphere. At that time, massive ice sheets, known as the Laurentide and Scandinavian ice sheets, reached thicknesses of up to 3 kilometers, stretching from Canada to Scandinavia and covering vast territories, including much of modern-day United States, Canada, and Northern Europe. Glaciers, moving on their bases, shaped landscapes, creating valleys and lakes such as the Great Lakes in North America, which formed as a result of the melting of these glaciers. Sea level at the time was significantly lower than today's levels, approximately 120 meters, as a large portion of the water was frozen in the glaciers. This opened up new land masses, such as the Bering Land Bridge, which connected Asia and North America, allowing the migration of animals and people. In the harsh climate, where temperatures in northern regions dropped to -30 degrees Celsius, climate zones underwent significant changes. Tundras and steppes, stretching before the ice front, became home to specific fauna of the glacial period, including mammoths, woolly rhinos, and bison. These mammals adapted to the cold climate, having thick fur and a layer of fat beneath the skin for protection against the cold. In the tundras, low-growing plants such as mosses and lichens thrived in the short growing season. Despite the harsh conditions, these ecosystems supported complex food chains, and the remains of animals like mammoths indicate that they were primary targets for ancient humans who used their bones and hides for their needs. Archaeological finds, such as those in the Wilder's Cave in Denver and excavations in Siberia, confirm that people used tools and technologies that allowed them to survive in these harsh conditions. At this time, not only were there changes in ecosystems, but also transformations in climate that later led to the retreat of glaciers and the beginning of a new climatic period. As a result, by the end of the last glacial maximum, which concluded around 12,000 years ago, the climate became significantly warmer, and glaciers began to melt rapidly, radically altering the Earth's landscape and leading to the formation of modern landscapes. The megafauna of the last ice age was incredibly diverse and impressive. For instance, mammoths could reach heights of up to 4 meters and weigh up to 6 tons. These giant herbivores, covered in long fur and possessing distinctive curved tusks, inhabited vast expanses of North America and Eurasia. They fed on grasses, shrubs, and small trees. Unlike modern elephants, mammoths were adapted to cold climates, and their shaggy hides helped them survive harsh winters. Woolly rhinos, similar in size to mammoths, also had a powerful build and long fur that protected them from the cold. These mammals lived in the same ecosystems as mammoths and played a crucial role in maintaining the balance of nature by eating grasses and creating open spaces necessary for other species. Cave bears, which lived during this time, were among the largest land predators, reaching lengths of over 3 meters. They could weigh up to a ton and were adapted to cold conditions, using caves as shelter. Their diet consisted mainly of plant food, but they also hunted other animals, making them important predators in the ecosystem. Saber-toothed cats, with their characteristic long canines, became a symbol of the megafauna. These predators were generally smaller than modern lions, but had powerful jaws and an adapted body structure that made them excellent hunters. They preyed on large herbivores like mammoths and rhinos, using their agility and strength. In open landscapes, they could move quickly and sneak up on prey, making them effective hunters. These animals interacted with each other, forming complex ecosystems where herbivores sustained vegetation and predators controlled the populations of their prey. The existence of megafauna is confirmed by numerous fossil finds and artifacts dating back to the last ice age, which lasted from 100,000 to 12,000 years ago. During this time, climate changes significantly impacted their lives as temperatures began to rise and ecosystems began to transform, ultimately leading to the extinction of many megafauna species. Mammoths disappeared around 3,000 years ago, being the last representatives of their kind, and the reasons for their extinction are still actively debated by scientists. At the end of the Pleistocene epoch, approximately 13,000 years ago, the mass melting of glaciers began, covering a significant portion of North America and Eurasia. This process freed up vast territories from the ice cover, creating new ecosystems and altering the landscape. Glaciers such as the Laurentide and Scandinavian ice sheets retreated, leaving behind moraines and lakes. For instance, the current Upper Lake, one of the world's largest freshwater lakes, was formed in the area that once held extensive water bodies stretching over more than 9,000 square kilometers. By the end of the last glacial period, the global sea level rose by about 100 meters compared to the level during the maximum glaciation, leading to the flooding of coastal areas and the formation of new river systems. For example, the Mississippi River took its modern form due to the melting of glaciers, which changed its course and increased its water flow. With the retreat of the ice, forests gradually advanced northward, replacing tundra and taiga. In the area that is now Canada, pine and birch forests began to displace moss and grassland ecosystems, creating new habitats for animals and plants. At this time, species such as spruce and fir became dominant in the northern forests. As temperatures increased and the area of glaciers decreased, ecosystems adapted to the new conditions. Research shows that over the period from 12 to 10,000 years ago, the climate became warmer, contributing to an increase in biodiversity. As a result of these changes, numerous new flora and fauna species emerged, such as dwarf forests on northern slopes and extensive grassland ecosystems that supported a variety of herbivores and carnivores. For example, on the vast expanses freed from the ice, animals such as bison, deer, and various bird species began to inhabit the area. Thus, the melting of glaciers became a catalyst for profound changes in ecosystems, shaping the modern landscape of the Northern Hemisphere. On some territories, unique ecosystems such as tundra meadows formed, where plants adapted to a short growing season coexisted with animals that migrated in search of food. This process continued until the beginning of the Holocene epoch, when the climate became more stable, facilitating the further spread of forests and an increase in biodiversity. Scientific research shows that at this stage, significant changes occurred in the distribution of species, which in turn affected the migration routes of animals and their interactions with each other. The melting of glaciers marked the start of a new chapter in Earth's history, as ecosystems began to adapt to new climatic conditions, laying the foundation for modern biodiversity. During the melting of glaciers, especially during the last glacial maximum, catastrophic floods occurred due to the breaches of glacial lakes. These lakes, formed as a result of the accumulation of meltwater, sometimes became real-time bombs. For instance, in the area of modern-day Scotland and Iceland, glacial lakes such as Lake Lagungur reached colossal sizes and held back enormous volumes of water. When the dams, made of ice and mud, could no longer withstand the pressure, a powerful breach occurred. Millions of cubic meters of water rushed down the slopes, causing instantaneous and devastating floods. One of the most famous events happened around 10,000 years ago in North America, when the breach of Lake Missouri caused catastrophic floods in the Mississippi River Valley. Research shows that as a result of this event, water moving at speeds up to 30 kilometers per hour eroded the soil and created new canyons and valleys in just a few days. As a result, a specific landform known as a scabland was formed. This term is used to describe areas where extensive soil erosion and the formation of new landscapes occurred due to the incredible power of water. For example, in modern-day Norway, where powerful glaciers once existed, deep and narrow valleys were formed, now known as fjeld. Meltwater created conditions for the formation of new ecosystems, but also for the destruction of existing ones. Such floods not only altered the landscape, but also had a profound impact on human settlements, as many of them were threatened. It is important to note that such catastrophes did not happen just once and were part of a broader cycle of climatic changes that continue to influence our planet. As a result of such events as glacial lake breaches, new landscapes and ecosystems were formed. And this process continues to leave its mark on the geological history of Earth. In just a few days or weeks, the power of water could completely transform the appearance of the land, serving as a reminder of nature's might. As a result, these floods not only left traces on the surface of the Earth, but also changed the very structure of the soil, forcing it to adapt to new conditions. At the end of the Pleistocene epoch, approximately 30,000 years ago, a process began that led to the extinction of megafauna, including impressive animals such as mammoths, mastodons, and giant ground sloths. This extinction affected a complex of species that played a key role in the ecosystems of their time. For instance, mammoths were not only large herbivores, but also crucial for maintaining vegetation in tundra landscapes. Their disappearance was largely linked to climate changes when global warming began, causing glaciers to melt and altering vegetation. This change in habitat became critical for many large mammals that could not adapt to the new conditions. For example, mastodons, which lived in forested and boggy areas, also faced a reduction in their habitat, leading to a decrease in food availability. One of the factors contributing to the extinction of megafauna was also human pressure. As Homo sapiens migrated across the planet, they began hunting these giants using primitive tools. Archaeological findings confirm that people hunted mammoths and mastodons, leaving behind bones and tools that indicate these animals were a significant source of food and materials for early humans. For example, in places where mammoth remains were found, archaeologists discovered evidence of hunting, such as stone arrowheads dating back to around 15,000 years ago. Simultaneously, climate changes created conditions for the spread of new plant and animal species that could outcompete or displace megafauna. The direct impact of humans combined with climate changes led to the rapid transformation of ecosystems that had existed for millions of years. For instance, giant ground sloths living in the forests of Central and South America could not adapt to the disappearance of their usual vegetation, nor to the presence of humans who began hunting them. As a result of this multifaceted pressure, by 10,000 years ago, megafauna could no longer exist in their original forms. These changes not only affected the extinction of individual species, but also led to structural changes in ecosystems that had previously been stable. The disappearance of these large mammals allowed smaller predators and herbivores to occupy the vacant niches, altering the dynamics of food chains. For example, the disappearance of mammoths could have led to an increase in the numbers of some herbivore species that had previously been under competitive pressure. The unique ecosystems of the Pleistocene, which were home to megafauna, could no longer recover, and new communities began to form in their place. The events of this time did not merely mark the end of the megafauna epoch, but also shaped the evolution of ecosystems on Earth for many thousands of years to come. By the end of the last ice age, approximately 90% of megafauna species in North America and around 80% in Europe had gone extinct. Meteorite craters are enduring traces of cosmic impacts that have been preserved in Earth's geological record, testifying to the constant interaction of our planet with the cosmos. Each crater is the result of a collision between a meteorite, asteroid, or comet and Earth, and these events occur much more frequently than might initially appear. According to astronomers' estimates, Earth encounters meteorites with a total mass of around 100 tons each year, although only a small fraction of them reach the surface as noticeable objects. Impacts capable of creating craters are less frequent, but their consequences can be catastrophic. It is known that approximately 70 million years ago, at the end of the Cretaceous period, A collision with an asteroid about 10 kilometers in diameter led to mass extinction, resulting in the disappearance of dinosaurs and many other species. Meteorite craters form due to processes involving enormous energies generated during collisions, when the speed of the object can reach tens of kilometers per second. These impacts cause not only physical destruction, but also catastrophic changes in the atmosphere and climate. In the geological record, such events leave clear traces that scientists study to understand Earth's history and its vulnerability to cosmic threats. Craters can be found in the most diverse locations, from remote deserts to oceanic depths, and their study helps us understand how Earth interacts with its environment. Using radiometric dating and analysis of the mineralogical composition of craters, scientists can determine the age of the events and their consequences for ecosystems. For example, craters can contain rare minerals and fossils that help reconstruct the picture of the time when the collision occurred. In some cases, craters become places of unique geological processes where new mineral species emerge, further highlighting how interaction with the cosmos influences our planet. Extensive research on meteorite craters, conducted using satellite technology and geophysical methods, shows that even small impacts can have significant consequences for the climate and life on Earth. It is important to note that most meteorites burn up in the atmosphere, but those that reach the surface can cause devastating consequences. Meteorite craters are not only geological formations, but also reminders that Earth is constantly subjected to cosmic influences, and the vulnerability of our planet to natural forces remains a topic of ongoing study. There are more than 300 known craters in the world, but many of them have not been studied, and scientists continue to uncover new facts about the history of collisions. Meteorite impacts leave behind not only craters, but also changes in ecosystems that can last for millions of years. Studying such changes helps us understand how life on Earth has adapted to the extreme conditions created by cosmic impacts. Craters formed as a result of such collisions serve as important markers in Earth's geological history and provide a window into the past of our planet. The meteorite crater known as the Arizona crater is an impressive geological formation with a diameter of approximately 1 kilometer and a depth of more than 200 meters. This crater, which is relatively young in geological terms, formed around 50,000 years ago as a result of a meteorite impact. The meteorite, with a diameter of around 20 meters, struck the Earth at a speed of approximately 20 kilometers per second, creating a massive crater that can be seen from space. The crater's excellent state of preservation is due to its size and location in the Arizona desert, where erosion is minimal due to the lack of rainfall. Standing at the edge of the crater, visitors feel small in comparison to this giant wound in the Earth's surface. The scale of the event that created this crater is awe-inspiring, serving as a reminder of the power of the cosmos and the impact that meteors can have on our planet. The layers of rock visible within the crater reveal millions of years of geological history, creating a strong sense of time and space. One of the most striking visual impressions is the contrast between the dark basaltic rocks and the light sandstone, adding depth to this natural wonder. The crater has become a popular tourist destination and a subject of scientific research, attracting attention not only for its size, but also for the unique opportunities it offers for study. The complex structure of the crater continues to be studied by geologists who are interested in understanding how such events affect ecosystems and climate conditions over the long term. The Arizona crater also serves as a site for various experiments related to the impact of meteorite strikes on Earth. Research conducted in this crater helps model how other planets might react to similar events. The height of the crater walls creates an effect of a cliff, enhancing the sense of its grandeur and depth. Looking down into the crater reveals a breathtaking sight. The crater floor is covered with debris from the impact, and surrounding it are rock formations that tell their own geological story. The presence of this crater on Earth serves as a reminder that our planet has been and continues to be subjected to attacks from space. This wound on the Earth's surface not only impresses with its scale, but also serves as an important reminder that we live on a planet that is constantly changing. It is worth noting that the crater is part of a national park and is protected, ensuring its preservation for future generations. Visually, it appears as a massive bowl surrounded by walls of unweathered rock, which emphasize its age and history. Pop-Ugai crater is one of the largest impact craters on Earth, located in a remote part of Siberia, in the region of Yakutia. Its diameter is approximately 120 kilometers, and its age exceeds 140 million years. This crater was formed as a result of a powerful asteroid impact, which, according to estimates, had a diameter of about 5 kilometers. The impact was so strong that it caused massive changes in the surrounding environment, including the release of a large amount of dust and debris into the atmosphere. This could have led to global climate changes and even mass extinctions. Pop-Ugai crater is surrounded by inaccessible forests and taiga, making its study a true challenge for scientists. Although the crater was discovered in the mid-20th century, its study began only in the late 1980s, when Soviet geologists conducted detailed research on this unique structure. During these studies, unique impact diamonds were discovered, formed as a result of high temperatures and pressures during the impact. These diamonds, known as impact diamonds, differ significantly from ordinary diamonds as they are formed under conditions that cannot be replicated in a laboratory. Specifically, they have characteristic inclusions and unusual shapes, making them valuable not only for scientific research, but also for the jewelry industry. Studies show that Pop-Ugai crater contains approximately 30 tons of impact diamonds, making it one of the richest places in the world in terms of this indicator. Scientists have determined that these diamonds are between 7 and 30 million years old, indicating that they formed after the impact and have survived a long process of erosion and movement across the surface. The discovery of such diamonds has attracted the attention of geologists from around the world, and their research continues. It is important to note that Pop-Ugai crater is under state protection, which helps preserve its unique characteristics and prevent human interference. The complex conditions of access to the crater also contribute to its preservation. The crater is surrounded by high mountains and rivers, making its study a labor-intensive process requiring significant efforts and resources. Since this place bears the traces of a cosmic catastrophe that occurred tens of millions of years ago, it continues to be an object of interest for scientists eager to unravel its mysteries. In recent years, detailed geological research has been conducted here, which helps better understand the impact of meteorite impacts on the planet and the evolution of life on Earth. These studies show how such catastrophes can shape landscapes and create new ecological niches. Pop-Ugai crater is not just a geological formation, it is a testament to ancient events that could have changed the course of Earth's history. Scientists hope that further research will help determine how the impact occurred and what changes it caused in the ecosystems of that time. The Tunguska event occurred on June 23, 1908, in a remote Siberian taiga, and its consequences continue to raise many questions. That day, a powerful explosive phenomenon, equivalent to several megatons of TNT, occurred in the sky over the region between the Vitim River and Lake Baikal, wiping out approximately 2,000 square kilometers of forest. According to scientists, the explosion was audible up to 1,000 kilometers away, and the brightness of the light wave was so great that it could be observed even in the European part of Russia. Remarkably, despite the colossal explosion, no crater was formed, which challenges conventional notions about celestial bodies and their interaction with the atmosphere. Researchers suggest that this could have been the result of a meteorite breaking up in the atmosphere at an altitude of 5 to 10 kilometers. But the exact causes and mechanisms of the phenomenon remain unclear. The complexity of the research is exacerbated by the fact that the site of the event is located in a hard-to-reach zone, and the first expeditions encountered numerous difficulties, including wild nature and the absence of infrastructure. The first scientific groups, such as the team led by geologist Viwa Modest in 1930, attempted to conduct research, but due to the remoteness and harsh working conditions, they were able to collect only limited data. Over the years, the mystery of the Tunguska event has attracted more and more researchers, from Soviet scientists to international teams trying to unravel this unique puzzle. In 1991, after the dissolution of the Soviet Union, new technologies became available, allowing for more detailed research, including soil analysis and the study of fossils found in the blast zone. Despite the efforts, many aspects of the event remain unclear, including the composition of the object that caused the explosion and its exact size. Some researchers even proposed that it could have been something more than just a meteorite, including ideas about alien spacecraft or interference with other dimensions. None of these hypotheses have solid evidence, adding to the enigma of this event. In 1999, to mark the centennial of the event, an international symposium was held, where scientists exchanged data and new theories, demonstrating the lively discussion of this phenomenon. The scientific community continues to study the Tunguska event, aiming to understand what lessons can be learned from this catastrophic event and how it can help in preparing for possible future cosmic threats. Around this event, a unique atmosphere of scientific mystery has been created, which continues to attract the attention of researchers even more than a century later. The extent of the destruction was so great that some trees were felled in a radius of up to 100 kilometers from the epicenter, and in the center, a kind of dead zone formed, where not a single living tree remained. On February 15, 2013, the Chelyabinsk meteor, which entered Earth's atmosphere, served as a stark reminder of how sudden cosmic threats can intrude into our daily lives. As the meteor entered the atmosphere, it heated up to temperatures of around 3,000 degrees Celsius and, moving at speeds of approximately 40,000 kilometers per hour, produced a blinding flash comparable to the brightness of the sun. The shock wave from the explosion was so powerful that it circled the globe twice, and in Chelyabinsk, located several hundred kilometers from the epicenter, windows in homes shattered, and people panicked and rushed out onto the streets. As a result of the explosion, more than 2,000 buildings were damaged, with over 600 requiring major repairs, and the damage was estimated in the billions of rubles. More than 1,500 people sought medical help, many of whom were injured by flying glass. In the days following the event, a large-scale operation was launched in Chelyabinsk to search for meteor fragments. Groups of scientists and volunteers investigated Lake Chebakul, where it was believed part of the meteor could have fallen. Eventually, a large fragment, the size of a small car and weighing around 60 kilograms, was found in the lake and later recovered for study by Russian and international scientists. The Chelyabinsk meteor became not only an object of scientific research, but also a symbol of the vulnerability of our planet to cosmic threats that can arise at any moment. It reminded us that the cosmos is full of unpredictable phenomena, and even in the 21st century, humanity remains at risk from extraterrestrial objects. The collision with the meteor showed that even the most modern cities are not protected from such disasters, and that our world can be at risk at any moment. Interestingly, this event not only sparked scientific research, but also raised questions about early warning systems and how humanity can protect itself from future cosmic threats. As scientists continue to study the fragments, seeking answers about the origin and composition of the meteor, it becomes clear that the Chelyabinsk meteor will remain in history not only as a physical object, but also as a significant lesson for future generations about the fragility of our safety under the cosmic sky. Tsunamis are giant waves that occur as a result of underwater earthquakes, landslides, or even meteorite impacts. These waves can reach heights of more than 30 meters, and their speed in open ocean can exceed 100 kilometers per hour. The main cause of tsunami formation is the sudden displacement of water caused by powerful underwater tectonic processes. For example, when tectonic plates collide, one plate may rise while another sinks, creating immense pressure in the water column. This pressure leads to the formation of waves that can travel vast distances across oceanic expanses, often remaining nearly invisible to ships on the surface. In open ocean, the height of a tsunami can be just a few dozen centimeters, and only specialized instruments can detect their movement. However, as these waves approach shallow water, they begin to grow in height, losing speed but increasing in power. This process is known as run-up. When the waves reach the shore, they can crash with devastating force, sweeping away buildings, trees, and vehicles. It is important to note that tsunamis can occur not only due to earthquakes, but also as a result of landslides, when large masses of earth fall into the ocean, creating a similar effect. Impacts from large meteorites that hit the ocean can also generate powerful tsunamis. For instance, it is believed that the impact with an asteroid that occurred 65 million years ago led to the mass extinction of dinosaurs, including through the generation of tsunamis that covered vast areas of land. Unlike ordinary waves, tsunamis possess such destructive power that they can move massive rocks and even sweep away entire cities. Underwater earthquakes, which are the primary cause of tsunamis, occur on the boundaries of tectonic plates. For example, the Ring of Fire in the Pacific Ocean is where numerous earthquakes take place. Interestingly, even several hours after an earthquake, when it seems the danger has passed, a tsunami can suddenly strike the shore, causing catastrophe. Tsunamis not only spread rapidly across the ocean, but also have a unique structure. They can consist of several waves, with the first wave not always being the most powerful. The potential for occurrence at any moment makes tsunamis one of the most dangerous natural phenomena. The deceptive calm of the ocean, when it appears completely peaceful, is misleading, and it is this calm that precedes the appearance of destructive waves, making tsunamis particularly treacherous. To date, the highest recorded tsunami was 160 meters tall, which occurred in Norway in 1920 when a landslide fell into a fjord. On December 12, 2004, one of the most devastating tsunamis in history occurred in the Indian Ocean. This natural disaster was a consequence of a powerful earthquake with a magnitude of 9.1 on the Richter scale that struck off the coast of Sumatra, Indonesia. The earthquake occurred at a depth of approximately 30 kilometers in a subduction zone where the Indian plate collided with the Burmese plate. As a result of this massive tectonic shift, waves were generated that raced across the ocean surface at speeds of up to 30 meters per second, akin to jet planes. The tsunami reached the shores of Indonesia within 15 to 30 minutes of the earthquake and then continued its path to other countries, including Sri Lanka, the Maldives, the Indian subcontinent, and even the coasts of Africa. As the waves approached the shore, their height significantly increased due to changes in the underwater topography and the shape of the coastline. In areas with flat seafloors and wide shallows, the waves accelerated, gaining strength, while in narrow bays and on steep cliffs, the waves reached their maximum height. The hardest hit regions included the province of Aceh in Indonesia, where the waves reached heights of more than 30 meters, and the coast of Sri Lanka, where the waves caused catastrophic destruction. In total, more than 230,000 people perished across the region. Millions were left homeless, and tens of thousands were injured. The damage from the destruction was estimated in the billions of dollars. Rescue operations continued for weeks, and the international community mobilized to provide assistance to the affected. Years after the tragedy, scientists continued to study the aftermath of the tsunami to better understand its mechanisms and develop early warning systems. The events of that day served as a lesson for the entire world about the destructive power of nature and the need for preparedness in the face of such disasters. The tragedy demonstrated how quickly the ocean can transform from a peaceful and serene body of water into a relentless destroyer, and how important it is to consider geological processes that can lead to such catastrophes. The tsunami of 2004 caused catastrophic changes to the coastal ecosystems. Mangrove forests, which played a crucial role in protecting the shores and maintaining biodiversity, were virtually destroyed. For instance, on the Indonesian island of Sumatra, which suffered the most, the area of mangrove forests decreased by 35% in the first months after the disaster. These forests were home to numerous species of animals, including rare birds and marine creatures, and their loss led to a significant decline in populations. Coral reefs, which also suffered from the powerful waves, lost up to 50% of their coverage in some areas. Studies show that corals subjected to severe impact often do not recover for many years, threatening not only marine life, but also local fishing communities that depend on these ecosystems. Salinization of agricultural lands became another critical consequence. As a result of flooding with saltwater, more than 100,000 hectares of land, previously used for rice and other crops, became unsuitable for farming. Farmers who previously could feed their families and sell surpluses on the market found themselves facing hunger and poverty. Additionally, the change in landscape caused by erosion and the movement of large volumes of sand and gravel made it difficult to restore normal ecosystems. On some coastal areas, new, smaller lagoons formed that could not support the previous types of life. However, amidst these destructions, nature began to slowly recover. On some sites where mangrove forests were destroyed, natural saplings began to grow, offering hope for ecosystem recovery. For example, in 2006, projects for planting mangrove trees were launched on the Thai coast, involving local communities in the restoration of affected areas. Coral reefs also began to show signs of recovery, although this process may take decades. In some places, scientists noted an increase in the number of juvenile fish and other marine creatures, indicating ecosystem recovery, but requiring constant monitoring and protection. The restoration of landscapes and ecosystems after such a destructive event as a tsunami is a long process that requires time, effort, and resources. But it demonstrates the resilience of nature in the face of catastrophe. For many years after the tragedy, researchers continued to track changes in ecosystems to better understand how to restore the natural balance and support life in these areas. Palico tsunamis, or ancient tsunamis, have left significant traces in the geological record that contemporary geologists study to gain insights into the frequency and scale of these destructive events. Researchers employ various methods, including the analysis of sedimentary deposits, to identify and interpret the traces of ancient tsunamis. During such investigations, for instance, geologists often find layers of sand, clay, and other materials that differ in structure and composition from surrounding layers. These sediments may be the result of powerful waves that transported marine or oceanic materials onto land. In particular, in Japan and along the North American coast, such deposits dating back approximately 3,000 years have been discovered, indicating the presence of powerful tsunamis in this region. Scientists such as Dr. Daisuke Ito from Tokyo University analyze these layers to determine their age using radiocarbon dating, which helps reconstruct the temporal framework of the catastrophes. For example, a study conducted in 2006 found deposits in the Tokyo area that date back to ancient tsunamis that occurred around 2013 BCE. These data help assess how frequently such events occurred in the past. Geologists also use geophysical methods such as seismic tomography to gain a more comprehensive understanding of the structure of the ocean floor and possible tectonic processes that could lead to tsunamis. For instance, a study conducted in 2015 along the California coast revealed accumulations of sediments indicating multiple tsunami events over the last 10,000 years. These findings not only help understand historical events, but also in predicting future risks. Comparing data on the frequency and intensity of paleo-tsunamis with contemporary seismic activities allows scientists to create models that predict the likelihood of tsunamis in specific regions. For this, they use software that simulates wave propagation based on data about tectonic plates. For example, in 2017, such research identified a high probability of tsunamis along the coast of Chile, leading to improvements in warning systems. Studies of paleo-tsunamis not only help understand the geological history of Earth, but also play a crucial role in protecting modern settlements from potential threats. For instance, in 2018, layers were discovered on Hawaii, indicating a powerful tsunami that occurred more than 10,000 years ago, which led to a revision of building codes in coastal areas. Specialists use information about ancient tsunamis to create more reliable risk maps, allowing better preparation for future disasters. Earthquakes are sudden and powerful movements of the Earth's surface that occur due to the abrupt displacement of blocks of the Earth's crust. This process is known as tectonic movements and takes place at the boundaries of tectonic plates, which can move in various directions, spreading apart, approaching each other, or sliding relative to one another. When stress accumulates in the crustal materials and forces exceed the strength limit, catastrophic destruction occurs, releasing enormous amounts of energy. Energy released during an earthquake propagates as seismic waves, which are divided into two main types, longitudinal and transverse. Longitudinal waves, or P waves, move through the Earth, causing compression and expansion of materials, while transverse waves, or S waves, cause vibrations perpendicular to the direction of movement, making them more destructive. These waves travel at different speeds. P waves usually move faster and reach seismometers first, while S waves follow with a delay. The closer the epicenter of the earthquake to the surface, the stronger the vibrations are felt. On the surface, earthquakes can cause not only shaking, but also more complex phenomena such as seismic waves, which can lead to vertical and horizontal oscillations, creating additional loads on buildings and structures. Depending on the nature of the vibrations, they can be light, barely perceptible, or catastrophic, capable of destroying even the strongest constructions. For example, depending on the type of soil and geological conditions, vibrations can cause abrupt shifts in the foundations of buildings, leading to their tilting or collapse. These phenomena can occur at any time, and they are impossible to predict, making them particularly dangerous. Interestingly, even small earthquakes can cause significant damage in the case of poor construction. Seismic activities can also cause secondary effects such as landslides or tsunamis, adding to the overall threat. More than 300,000 earthquakes are registered worldwide each year, but most of them are too weak to cause any noticeable consequences. At the same time, powerful earthquakes can reach magnitudes of 9 or more on the Richter scale and higher, leading to catastrophic consequences, as was the case in 2011 in Japan, when an earthquake of magnitude 9 caused a tsunami, leading to an accident at the Fukushima nuclear power plant. Knowledge of the mechanisms of earthquakes and their consequences plays a crucial role in the development of protection and warning systems to minimize damage and save lives. On November 18, 1755, Lisbon, the capital of Portugal, was struck by a catastrophic earthquake with a magnitude of around 9 on the Richter scale. This event was one of the most devastating in European history, claiming the lives of approximately 100,000 people and destroying around 90% of the city's buildings. Within minutes, massive earth waves, resembling the fury of nature, razed homes, churches, and palaces, which were built in the grand architectural style of the time. However, this was just the beginning of the calamities. Soon after the earthquake, a powerful tsunami hit the coast of Lisbon, with wave heights reaching 30 meters, sweeping everything in its path and exacerbating the damage caused by the earthquake. Fires, ignited by the destruction, spread to the remaining buildings, adding to the chaos and panic that gripped the city. Firefighting teams, if they existed, were unable to control the fire, which quickly spread throughout the city, turning Lisbon into a sea of flames and smoke. This event not only shook the physical structure of the city, but also the European society as a whole. Philosophers and thinkers, such as Voltaire and Candide, began actively discussing the nature of evil and divine providence, questioning how such a terrible disaster could have occurred. Voltaire, in his work Candide, mocked the optimism propagated by philosopher Leibniz, asserting that there is nothing good in this world. This earthquake served as a catalyst for philosophical debates about the meaning of suffering and the role of God in human life. Additionally, it stimulated the development of seismology as a science. Scientists like the seismologist A.D.G. Dupuy began systematically studying earthquakes, their causes and effects. This event also led to the creation of new building codes and regulations aimed at reducing damage from future natural disasters. The need for more earthquake-resistant structures emerged, fundamentally changing the approach to architecture and urban planning in Europe. The Lisbon earthquake was not only a tragic event, but also a significant milestone in the history of science and culture. The total area of destruction was approximately 7 square kilometers, clearly demonstrating the scale of the catastrophe and its impact on the future. In April 1906, San Francisco was devastated by a catastrophic earthquake caused by the San Andreas Fault, which stretched over 800 kilometers along the California coast. Earthquakes measuring up to 8 on the Richter scale, recorded at 4:30 a.m., shattered the city, leaving behind chaos and destruction. Within the first few seconds, the ground shook, buildings trembled, and older structures collapsed, resulting in numerous casualties. Estimates suggest that around 3,000 people died, and more than 12,000 were injured. However, the true catastrophe unfolded later when fires broke out due to damaged gas pipelines and stoves. The fire spread rapidly, turning the city into a burning ruin. Within the first day after the earthquake, over 400 separate fires were registered, burning with such intensity that firefighters could not control them. Exhausted firefighters became victims of their own efforts as the flames consumed entire neighborhoods, including historic buildings and residential areas. As a result, many survivors lost their homes and property, with the total area of destruction exceeding 14 square kilometers. The situation was further exacerbated by a shortage of water, as damaged water mains could not provide sufficient pressure to fight the fires. Residents tried to extinguish the fires on their own, but this only added to the chaos. Over the course of 3 days after the initial quake, the fire consumed more than 90% of the city, and by April 5th, 80% of buildings were destroyed or burned. The city's unique architecture, including the beautiful Victorian Painted Ladies District and the famous Marble City Hall, was trapped in the inferno. The remains of burned buildings served as a stark reminder of how quickly one can lose what was built over decades. The city's reconstruction took years, and many residents never returned to their former homes. This catastrophic event marked the beginning of a new era in construction, with a focus on earthquake-resistant technologies. This incident became a crucial lesson for the world about how natural disasters can not only alter the landscape, but also change the fate of entire cities and their inhabitants. San Francisco has experienced more than 30 major earthquakes since then, but none have left as deep an imprint on history as the 1906 earthquake. The development of seismic-resistant construction has been a direct response to the devastating earthquakes that have claimed numerous lives and destroyed entire cities. Engineers and architects began to study how buildings react to underground tremors and developed methods to minimize damage. One of the first steps in this direction was the implementation of damping technologies that allow buildings to absorb vibrations. For example, in the 90s, Japan actively began using active damping systems, where special devices, similar to gyroscopes, help stabilize structures during earthquakes. In 2000, the Tokyo Skytree was built, which uses a unique technology called passive damping, a system based on the use of heavy masses that counteract the building's vibrations. An important aspect of seismic-resistant construction is the creation of flexible structures that can deform and return to their original position without damage. In 2005, the One Rincon Hill residential complex in San Francisco was put into operation using a flexible steel frame that can absorb and dampen seismic loads. The use of special materials, such as high-strength concretes and fiberglass reinforcement, has become a standard in modern construction. These materials not only increase strength, but also reduce the weight of the structure, which is critically important in seismically active zones. In 2012, after a devastating earthquake in New Zealand, new building codes were developed that require the use of seismic-resistant technologies in new buildings. As a result, in Christchurch, residential buildings were constructed using a special foundation isolation system that allows buildings to float during underground tremors and reduces the risk of damage. The use of computer modeling has also become an important tool in the design of seismic-resistant buildings. Architects can test their designs in advance to see how they will behave under various earthquake scenarios. For example, in 2018, a simulation was conducted in Los Angeles that showed buildings based on new technologies could withstand an earthquake of magnitude 7.0 or more. It is important to note that such buildings not only protect people, but also reduce economic losses by minimizing damage and property loss. Monitoring systems installed in new buildings allow real-time tracking of their condition and warning of potential risks. For example, in 2020, California implemented a system that uses sensors to monitor the condition of buildings after earthquakes to quickly assess damage and take action. The use of three-dimensional design and modern technologies also allows for the creation of buildings that are not only safe, but also aesthetically pleasing, which is important for modern urban design. Furthermore, in recent years, architects have begun to consider the possibility of integrating seismic-resistant technologies into historical buildings, which requires a special approach and respect for architectural heritage. In 2020, in Iran, a successful renovation of a historical building was carried out, which applied modern technologies while preserving its historical value. Ultimately, the development of seismic-resistant construction has been a significant step in ensuring the safety of citizens and preserving cultural heritage, as demonstrated by the examples of many cities striving for sustainable development. Early warning systems for earthquakes have become an indispensable tool in the fight to preserve human lives, particularly in seismically active regions such as Japan, where a devastating earthquake of magnitude 9 in 2011 led to the Fukushima disaster. In Japan, a comprehensive network of seismographs consisting of over 3,000 sensors continuously monitors the Earth's crust in real time. These devices can detect even the slightest tremors that may precede more powerful seismic events. The data from these seismographs are processed using complex algorithms developed by scientists at Tokyo University, which can assess the strength and location of an earthquake in just a few seconds. For instance, an algorithm called Quick Shake analyzes the data and issues a warning within 3 to 4 seconds after the onset of tremors, allowing for the initiation of public alerts. A crucial aspect is the communication system, which sends messages through various channels, from text messages to mobile phones to audible signals in public places. In Japan, such alert systems, known as J-Alert, provide immediate notification to citizens of impending danger. These signals can be heard over significant distances and convey information about the need to seek shelter in safe locations. In 2013, the J-Alert system was enhanced, reducing the warning time to 1 to 2 seconds. The effectiveness of these systems is evident in the statistics. According to the Japanese government, the improved early warning system has reduced the number of casualties by 30%. Despite the high degree of automation, human factors play a significant role. Specialists working in data processing centers must be ready for emergency situations and capable of making quick decisions under stress. This is not just a job, but a race against time, where every second can be critical. In countries like Chile, similar systems have been implemented using seismograph data to warn the public of impending threats. Chile's tsunami warning system, launched in 2005, actively uses seismograph data and provides alerts through television and radio channels, as well as through sirens. The success of such systems depends on the clear coordination between various government agencies, which requires ongoing training and preparation of specialists. In the 19th century, such systems did not exist, and earthquakes claimed thousands of lives, such as in San Francisco in 1906, when a devastating earthquake and subsequent fire resulted in the deaths of more than 3,000 people. Today, thanks to modern technologies, we have the opportunity to minimize the impact of natural disasters. For example, in 2020 in Turkey, after an earthquake of magnitude 6.5, the early warning system provided a warning to residents 10 seconds before the main tremors, allowing many people to find shelter and avoid serious injuries. Such examples demonstrate how technology can save lives if properly integrated into the healthcare and civil defense systems. Early warning systems are not just technical devices, but part of the culture of safety that must be developed and maintained at an appropriate level, so that every citizen knows how to act in case of an earthquake. The climate of Earth has undergone numerous changes throughout its geological history, demonstrating remarkable variability that has become a defining feature of our planet. Over millions of years, Earth has experienced cycles of greenhouse states, during which surface temperatures significantly increased, allowing tropical forests to thrive even in regions now covered in ice. For example, during the Cretaceous period, approximately 130 million years ago, the level of carbon dioxide in the atmosphere reached values exceeding 400 parts per million, contributing to the creation of a warm climate with extensive seas and rich flora and fauna. At this time, giant reptiles such as the Tyrannosaurus rex inhabited environments far removed from today's polar regions. These warm periods were followed by ice ages, when Earth plunged into cold cycles, leading to the formation of vast ice sheets that covered significant areas, including much of North America and Europe. During these times, sea levels fell and the climate became harsh, limiting the spread of life. For instance, during the last ice age, which ended around 10,000 years ago, the planet's temperature was several degrees lower than today, resulting in the formation of ice shields in Canada and Scandinavia. These ice shields reached thicknesses of up to 3 kilometers and significantly altered the landscape, leaving behind characteristic relief features. The Earth's climate system functioned as a complex mechanism where even small changes in carbon dioxide levels could lead to catastrophic consequences, such as rapid warming or cooling. Research conducted by scientists shows that such temperature fluctuations are influenced by various factors, including solar activity, volcanic activity, and even changes in planetary orbits. For example, the Milankovitch cycles, which describe changes in the tilt and eccentricity of Earth's orbit, played a key role in initiating ice ages and interglacial periods. These cycles occur within a range of 20,000 to 100,000 years, demonstrating how long the climate can remain stable or undergo change. Global climate changes were also determined by feedback effects, where an increase in temperature led to the melting of ice sheets and the release of methane from permafrost, further intensifying warming. As a result, the climate of Earth is not just a set of numbers and data, but a whole history of changes, where each period has left its mark on ecosystems, shaping conditions for life. These changes occurred against the backdrop of slow but inexorable changes in continents, which also influenced climatic conditions. For example, when continents moved towards the equator, this contributed to a warmer climate, while their movement towards the poles could cause cooling. Cosmic factors, such as Earth's position relative to other planets, also contributed to climatic changes. Therefore, the climate of Earth is a dynamic, constantly changing system that has been shaped by numerous factors over billions of years. In this context, it is important to understand that present-day climate changes are merely a continuation of an ancient history in which Earth has repeatedly transitioned from warmth to cold. Scientific research shows that over the last 40,000 years, the planet's temperature has fluctuated within a range of 10 degrees Celsius, demonstrating its ability to change. The Paleocene-Eocene thermal maximum occurred approximately 56 million years ago and is considered one of the most significant climatic events in Earth's history. During this period, the ocean's surface temperature rose by 5 to 8 degrees Celsius, leading to substantial changes in both marine and terrestrial ecosystems. The primary cause of this warming is believed to be a sudden release of carbon into the atmosphere, likely due to volcanic activity, as evidenced by research conducted by geologists from Stanford University who analyzed the isotopic composition of carbonates deposited in oceans. The temperature increase resulted in significant shifts in the ranges of plants and animals, particularly the displacement of biomes. For instance, tropical forests began to spread to higher latitudes, accompanied by the disappearance of many cold-loving species. While today's tropical plants are primarily found in equatorial regions, during the Eocene, their ranges extended to areas such as the present-day Arctic. Fossil finds in Greenland, for example, indicate that palms and other heat-loving plants grew there. In marine ecosystems, the warming led to changes in the distribution of species, which in turn affected food chains. The rise in water temperature also contributed to the extinction of certain marine organisms, such as specific mollusks and corals, that could not adapt to the new conditions. Studies conducted by scientists from the Smithsonian Institution showed that the coral reefs of the Eocene epoch differed significantly in composition and diversity from today's reefs, with many species that are now rare or extinct being dominant. Meanwhile, some groups of organisms, such as mammals and birds, were able to quickly adapt to the new climatic conditions thanks to biological evolution. For example, the ancestors of modern elephants and whales adapted to life in the new ecosystems. The extensive forests that formed as a result of the warming became an ideal habitat for the reproduction and spread of various species, leading to an increase in their diversity. During this time, some mammals also increased in size, which can be attributed to more favorable conditions for their existence. Overall, the Paleocene-Eocene thermal maximum was a crucial stage in the history of life on Earth, demonstrating how climatic changes can profoundly impact the biosphere and its inhabitants. There is evidence that during this period, ecosystems became more sensitive to climatic changes, serving as a lesson for future generations about the importance of balance in nature. The Paleocene-Eocene thermal maximum, which occurred around 56 million years ago, was caused by a massive release of methane from methane hydrates located on the ocean floor. Methane hydrates are crystalline structures that form under high pressure and low temperature, where methane from underground sources binds with water molecules. As the ocean temperature increased due to initial climate warming, these methane hydrates began to melt, releasing vast amounts of methane into the atmosphere. Scientific research indicates that during this period, the level of carbon dioxide significantly increased, making the atmosphere more saturated with greenhouse gases. According to data collected by researchers such as Dr. James Hansen of NASA, the level of carbon dioxide reached approximately 350 parts per million, a significant increase compared to previous epochs. This release of methane, in turn, led to further warming, creating a positive feedback loop. When methane, being a more potent greenhouse gas than carbon dioxide, entered the atmosphere, it caused even greater temperature increases. This, in turn, facilitated further melting of methane hydrates, creating a chain reaction that destabilized the planet's climate system. For instance, as a result of such processes, the Earth's temperature could have risen by 8 degrees Celsius over just a few thousand years. This rapid change in temperature regime had a profound impact on ecosystems, leading to mass extinctions and changes in the biogeographic distribution of species. Oceans became more acidic, negatively affecting marine life, while terrestrial ecosystems underwent significant changes, leading to the migration and adaptation of species. Research conducted by scientists such as Dr. Gregory Benford indicates that such methane releases could have been caused by increased volcanic activity, which also could have released carbon compounds from the Earth's depths. All these factors created a unique historical epoch when the Earth's climate system experienced sharp fluctuations, forcing its inhabitants to adapt to changing conditions. Today, we see that processes that occurred millions of years ago can serve as a lesson for the present, demonstrating how quickly climate changes can occur. For example, as a result of these changes, around 80% of all ocean-dwelling species could have gone extinct, highlighting the fragility of ecosystems in the face of rapid climate changes. Throughout the geological history of Earth, there have been hypothetical epochs known as Snowball Earth, during which glaciers covered almost the entire planet, including equatorial regions. These periods, dated approximately from 80 to 100 million years ago, were characterized by extreme climatic conditions, with the average temperature on the planet dropping to critical levels. In such conditions, oceans froze almost to the equator, creating an inhospitable world where life was threatened with extinction. Photosynthesis, the key process for sustaining life, almost ceased, as sunlight could not penetrate thick layers of clouds and ice. Studies show that during this time, the level of carbon dioxide in the atmosphere was extremely low, further exacerbating the situation. Life persisted only in isolated refuges, such as hot springs and deep-sea hydrothermal vents, which provided the necessary heat and chemical compounds for the survival of organisms. For example, in the Black Sea region, scientists discovered unique ecosystems where bacteria use hydrogen sulfide, emitted from the depths, to synthesize organic compounds, allowing them to survive in conditions completely unsuitable for other forms of life. In subglacial bodies of water, such as Lake Vostok in Antarctica, microbial communities were found that could exist in complete isolation from the external world for millions of years. These organisms adapted to extreme conditions, developing unique mechanisms for survival in cold and dark environments. The Snowball Earth period serves as a crucial example of how life can adapt to the most adverse conditions, as evidenced by the fossil findings that show how some species managed to survive this harsh climate. For instance, in layers of rocks formed during this period, the remains of organisms were found that served as the ancestors of modern marine creatures, such as starfish and sponges. Oceans during this period could be covered with an ice sheet up to several meters thick, adding additional stress to marine ecosystems. In some places, such as polar regions, glaciers reached thicknesses of more than 3 kilometers, making the planet's surface unsuitable for most forms of life. This harsh climate persisted for millions of years until changes in the level of carbon dioxide and temperatures led to global warming and the beginning of a new stage in Earth's history, when glaciers began to retreat, opening new possibilities for evolution and the development of life. The complex interactions between climate, atmospheric conditions, and ecosystems during this period underscore how, even in the most extreme circumstances, life finds ways to survive and adapt, reminding us of the deep interconnectedness of all processes on the planet. In summary, the hypothetical epochs of Snowball Earth serve as a significant reminder of how changeable the climatic conditions of our planet are and how they can influence life. During periods when Earth was in a state known as Snowball Earth, beneath the ice cover, crucial geological processes were taking place that would later alter the planet's climate system. Volcanoes under the ice began to actively release gases such as carbon dioxide and methane. These gases, entering the atmosphere, created a greenhouse effect, gradually warming the planet. Scientists note that over the past 50 million years, the level of carbon dioxide in the atmosphere fluctuated between 300 and 400 parts per million. But during the transition from Snowball Earth, it began to rise sharply. As these gases accumulated, the planet's temperature started to rise, leading to rapid melting of ice caps and glaciers. For instance, between 30 and 28 million years ago, Earth's temperature increased by 8 degrees Celsius over just a few thousand years. This melting led to significant changes in the landscape, opening up new lands and waters that had previously been hidden under multi-meter thick ice. Meanwhile, sea levels rose, flooding coastal areas and altering ecosystems that were just beginning to form in the warmer climate. Research shows that during the period between 30 and 20 million years ago, sea levels rose by approximately 100 meters, which was catastrophic for many marine and terrestrial species. During this time, other important changes also occurred, such as the expansion of tropical forests in equatorial regions, which contributed to increased biodiversity. In the face of these changes, there was active development of mammals and birds that began to occupy niches vacated by other species. Volcanoes continued to release gases, creating a new atmosphere where the greenhouse effect reached critical levels. Scientists such as Dr. John Mercer assert that this transitional period was a catalyst for the climate changes that would later lead to an era of more stable and warm climate. By 20 million years ago, Earth was no longer Snowball Earth, but had transformed into a world where climate conditions were significantly more favorable for life than ever before. It is important to note that the speed of these changes allowed many organisms to adapt to the new conditions, but also posed a threat to those that could not cope with the rapid climate fluctuations. The process of ice melt did not occur instantaneously, but stretched over several million years, gradually revealing new territories and ecosystems each year. Ultimately, around 30 million years ago, the climate reached a level where Earth became green and teeming with life. But this was the result of harsh changes that had occurred over millions of years as volcanoes, ice, and atmosphere interacted in a complex dance, reshaping the planet's very face. Massive extinction of animals and plants in the Anthropocene is a phenomenon characteristic of our time, when human activity leads to the disappearance of species at an unprecedented rate. According to scientists, the current extinction rate is tens and hundreds of times higher than the natural background level, which is approximately one extinction per million species per year. In recent decades, as reported by the Intergovernmental Panel on Climate Change, this process has accelerated to 30 species per day. The main factors contributing to this include the destruction of natural habitats, environmental pollution, climate change, excessive hunting and fishing, and invasive species that displace local ecosystems. For example, deforestation for agriculture and urbanization causes many species to lose their natural habitats, bringing them to the brink of extinction. According to the World Wildlife Fund, the number of wild animal populations has decreased by more than 60% over the past 40 years. This is a unique situation where one species, Homo sapiens, is causing a global ecological transformation that affects the biosphere on a scale without precedent in Earth's history. Humanity, in its relentless pursuit of economic development, has influenced the climate, which in turn alters the familiar habitats of many species. As a result of changes in temperature and sea level, as well as the frequency of extreme weather events such as hurricanes and droughts, species struggle to adapt to new conditions. Scientific research shows that ecosystems that were once stable are now fragile and prone to deep changes. For example, coral reefs, which are among the most diverse ecosystems on the planet, are suffering from massive bleaching due to ocean temperature rise and acidification, leading to the death of entire reefs and the disappearance of their inhabitants. The situation is exacerbated by the fact that many species cannot migrate to new territories because they encounter barriers such as cities, roads, and agricultural lands. Experts note that we are now on the brink of the sixth mass extinction, and its consequences will be felt for millions of years. Humanity, as it creates new technologies and expands territories, must remember that it can be both a destroyer and a protector of nature. Restoring ecological balance requires not only scientific knowledge, but also a change in people's attitude towards the world around them. It is important to understand that sustainable development is not just a fashionable term, but a necessity for the survival of both individual species and entire ecosystems. In the 21st century, we face challenges that can permanently alter the face of the planet if decisive action is not taken. Research shows that without significant efforts to protect nature and restore ecosystems, the future of many species remains uncertain. With the beginning of human migration to the Australian continent around 60,000 years ago, the epoch of the extinction of the megafauna of the Holocene also began. At that time, Australia was home to giant marsupials such as the Megatherium, which could reach lengths of up to 4 meters, and Diprotodon, the largest known marsupial mammal, weighing up to 2 tons. These animals evolved in isolation and had no natural predators except for large reptiles like the Megatherium. However, the arrival of humans changed the situation drastically. People brought with them hunting skills and fire, giving them a significant advantage as predators. Around 15,000 years ago, the megafauna began to disappear rapidly, coinciding with the arrival of humans, which many scientists attribute to intense hunting and changes in the ecosystem. The destruction of large herbivorous animals led to significant changes in the vegetation of Australia. In the absence of large mammals that largely controlled the vegetation, there was an increase in smaller shrubs and grasses. This also contributed to changes in the fire regime. With the increase in vegetation, there were more frequent and intense forest fires, which in turn made it more difficult for ecosystems to recover. Birds like the giant emu, which could once freely move across the continent, also became victims of the new conditions caused by human activity and hunting. These changes in the ecosystem clearly demonstrate how quickly and destructively ecosystem transformations can occur with the introduction of a new predator. Research shows that by the end of the last ice age, more than 30 species of large mammals had gone extinct on the continent. Climate change also played a role, but it was humans who became the catalyst for these processes, clearly illustrating the importance of preserving natural ecosystems. The disappearance of the megafauna not only altered biodiversity, but also had a long-term impact on the culture of indigenous peoples, who were forced to adapt to new conditions and hunt smaller animals. As a result, the Australian ecosystem, once rich in large species, was threatened, leading to the formation of unique but vulnerable ecosystems that we can observe today. It is important to note that such historical events underscore how human intervention can have irreversible consequences for ecosystems. The extinction of Diprotodon occurred approximately 10,000 years ago, and it was followed by other species such as the Megatherium and the giant marsupial wolf. Dodo, or dodo, was a flightless bird that inhabited the island of Mauritius. It became one of the most striking examples of the tragic fate of species that have become extinct due to human activities. When Europeans discovered the island in the 16th century, the dodo was completely unadapted to life in conditions where it was hunted and its habitat was being destroyed. The bird was quite large, reaching a height of 1 meter and weighing up to 12 kilograms. The dodo had no natural predators and was not afraid of humans, which ultimately led to its demise. In the first half of the 17th century, Dutch sailors began hunting dodos for food. The first descriptions of the dodo belong to the Dutch naturalist Willem van der Stel, who described the bird in 1611. However, hunting was only part of the problem. Swine, cats and rats were also introduced to Mauritius, which began eating dodo eggs and competing with them for resources. These introduced predators became a real scourge for the dodos, as the birds could not protect their nests from them. As a result, by the 1630s, the dodo had disappeared from the face of the earth. The last confirmed observations of the dodo were recorded in 1667. This happened less than 100 years after Europeans first set foot on the island. The bird, which once peacefully inhabited the dense forests and grasslands of Mauritius, became a victim of the lack of understanding of the value of a unique species. The disappearance of the dodo became a symbol not only of the loss of one species, but also of a broader problem, the loss of biodiversity, which occurs when humans interfere with ecosystems without considering the consequences. The dodo left behind only some fossil remains and descriptions, and its history serves as a reminder of how quickly a species can become extinct if the fragility of ecosystems is not taken into account. Excavations on Mauritius Island have uncovered dodo remains, confirming that its existence was terminated due to human activity and changes in the surrounding environment, including deforestation, where it lived. Modern methods of preserving endangered animal and plant species are gaining increasing importance in the face of global climate change and human activity. Captive breeding programs have become one of the key tools for restoring populations at risk of extinction. For example, the black rhino breeding program launched in the 1990s has increased the number of these animals from fewer than 100 individuals to more than 2,000 in the wild by the 2020s. Scientists from the International Union for Conservation of Nature, IUCN, are working to create sustainable populations that can return to their natural habitats. Genetic material cryopreservation opens up new horizons for preserving genetic diversity. Around the world, in laboratories such as the Biobank Center in Oklahoma City, scientists are freezing sperm, egg cells, and embryos of rare species, allowing these materials to be used for the reproduction of endangered animals in the future. For instance, in 2020, scientists successfully used frozen cells to clone a sea owl, which was previously considered extinct. Restoring ecosystems also plays a crucial role in preserving biodiversity. In the 2000s, Argentina launched a project to restore forests, which involved planting over 1 million trees and reintroducing endangered species such as jaguars and tapirs. Environmental organizations like WWF and Greenpeace actively support such initiatives, attracting funding and resources for projects aimed at restoring habitats. For example, in 2020, WWF launched a program to restore coral reefs in the Indian Ocean, which includes planting new corals and protecting existing ecosystems from human impact. These efforts are aimed at preventing new extinctions and preserving biodiversity for future generations. The importance of preserving species is underscored by the fact that each loss can have serious consequences for entire ecosystems. Restoring the populations of animals such as wolves and bears affects the balance in nature, preventing the excessive proliferation of other species. Scientific research shows that ecosystems with high levels of biodiversity are more resilient to changes and better adapt to conditions caused by climate change. In the 2020s, active measures are being taken in Europe to protect wild bee populations, which play a critical role in pollinating agricultural crops. In this context, programs to raise awareness and educate the public are becoming important. In the 2020s, the United States launched a project to teach school children about environmental protection methods, which covers more than 100 schools and involves thousands of children in practical actions to protect nature. The development of new technologies, such as DNA barcoding, allows scientists to better understand the genetic diversity and condition of animal and plant populations, facilitating more accurate planning of conservation efforts. As a result, the combined efforts of scientists, environmental organizations, and local communities are focused on preserving endangered species and restoring ecosystems, providing hope for a future where the diversity of life on the planet is protected. In particular, in 2020, China launched a program to restore the population of giant pandas, which includes protecting their natural habitat and developing ecotourism, allowing local communities to benefit from the conservation of nature. Anthropogenic climate change poses a serious threat to the planet, driven by human activities that intensify the greenhouse effect. This effect is caused by the accumulation of carbon dioxide and other greenhouse gases, such as methane and nitrous oxide, in the atmosphere, which absorb and trap heat emitted by the Earth. Since the beginning of the Industrial Revolution in the 19th century, the concentration of carbon dioxide in the atmosphere has increased by more than 40%, primarily due to the burning of fossil fuels, deforestation, and changes in land use. These processes not only increase the amount of greenhouse gases, but also disrupt the natural carbon cycles involving oceans, forests, and soils. For instance, research shows that oceans absorb around 30% of carbon dioxide, but their ability to do so decreases as water temperature rises, leading to further increases in atmospheric carbon dioxide concentrations. This creates a vicious cycle. Rising temperatures reduce the ocean's ability to absorb carbon, which in turn contributes to further atmospheric heating. The mechanism of climate change also includes human influence on other natural processes, such as the melting of glaciers and polar ice, which, according to climate scientists, is occurring at an unprecedented rate. Glaciers, containing frozen volumes of water, contribute to sea level rise when they melt, threatening coastal regions and ecosystems. Concurrently, changes in precipitation and temperature patterns put pressure on agriculture, causing droughts in some regions and floods in others. As a result, the planet's climate system becomes increasingly unstable, leading to changes in natural ecosystems and an increase in the frequency of extreme weather events, such as hurricanes and wildfires. For example, according to data from the World Meteorological Organization, the number of major hurricanes has increased by 40% over the past 30 years. This poses an additional threat not only to nature, but also to the lives and livelihoods of millions of people. The growing imbalance in the climate system becomes more apparent each year, with its consequences felt everywhere, from changes in animal migration patterns to threats to global food security. Humanity has entered an era where its actions directly influence the climate, and this necessitates urgent measures to halt the negative consequences. In the year 2000, scientists from the Intergovernmental Panel on Climate Change, IPCC, noted that without significant reductions in greenhouse gas emissions, the average global temperature could rise by more than 2 degrees Celsius by the end of the century. Every action, whether it is the use of renewable energy sources or reducing resource consumption, becomes crucial in combating this global problem. The melting of Arctic ice has become one of the most noticeable consequences of climate change, and its extent is impressive. According to data from the National Oceanic and Atmospheric Administration of the United States, the average area of sea ice in the Arctic has decreased by more than 40% since the beginning of the 2000s, and its average thickness has decreased by several meters. In particular, in 2018, scientists recorded the minimum area of ice in September, which was around 1 million square kilometers, the lowest value for that time of year. This process leads to the gradual replacement of the white surface of ice, which has high reflectivity, with the dark surface of open water, creating a positive feedback effect. Dark water absorbs more solar radiation, which in turn accelerates the melting of the remaining ice. This process intensifies warming in the Arctic, where temperature is rising twice as fast as the global average. This change in climate not only causes ecological problems, but also has a significant impact on local ecosystems. For example, changes in water temperature and oxygen levels affect the populations of fish, such as cod and herring, which are the main source of food for local residents. Indigenous peoples, such as Inuit and Chukchi, face a threat to their traditional ways of life, which depend on hunting marine mammals and fishing. In recent years, there has been a change in the migration routes of animals, which makes it more difficult to access traditional hunting grounds. Additionally, the melting of ice leads to an increase in the number of open water bodies, creating new shipping routes and opportunities for resource extraction, which also affects ecosystems and the way of life of local residents. There are even forecasts that by the end of the 21st century, the Arctic may become almost free of sea ice in the summer months, which will lead to significant changes in climate and ecosystems worldwide. Notably, according to the World Bank, around 30 million people worldwide depend on fishing and marine resources, which may be threatened by these changes. The loss of ice also affects sea level. According to research, each decrease in the area of ice by 1 million square kilometers can lead to a rise in sea level by several millimeters. It is important to note that these changes are occurring against the backdrop of a global trend towards warming, making the situation in the Arctic particularly critical and requiring immediate action to minimize the consequences. In 2000, scientists from the University of Alaska conducted a study that showed that the melting of Arctic ice can lead to changes in weather patterns in northwest North America, creating more frequent and intense precipitation. With each drop of melting ice, we lose not only our planet, but also important historical and cultural ties that have been formed over centuries in Arctic regions. Glaciers in Greenland and Antarctica are experiencing rapid changes that are causing global concern. According to NASA, the rate of ice melt in Greenland has increased by more than 30% since the beginning of the 2000s. This is due to the rise in temperature, which has increased by 2 degrees Celsius over the past 40 years, causing instability in the massive ice sheets. Meanwhile, in Antarctica, research conducted in 2009 shows that the rate of melting of the West Antarctic ice sheet has increased by 80% compared to previous decades. Scientists have found that warm ocean currents are penetrating under the ice sheets, accelerating their destruction. For example, the Thwaites Glacier, considered one of the most vulnerable, loses around 130 billion tons of ice per year. This glacier, the size of Florida, could raise sea levels by 3 meters if it were to completely melt. The movement of outlet glaciers, such as the Jakobshavn Glacier in Greenland, is also accelerating. It is now moving at a rate of around 30 meters per day, which is twice as fast as in the 1990s. This process leads to the formation of giant icebergs that break off from the main glacier. In 2018, scientists recorded an iceberg the size of London, which broke off from the Larsen Glacier, becoming one of the largest icebergs ever recorded. These massive ice formations moving into the ocean not only alter the landscape, but also affect marine ecosystems, creating new conditions for marine life. Each iceberg that drifts into the sea changes the salinity and temperature of the water, which can lead to changes in the migration of fish and other marine animals. The melting of glaciers also has a negative impact on global weather systems, as confirmed by research published in the journal Nature in 2020. Changes in the distribution of ice affect ocean currents, which in turn influence climatic conditions in Europe and North America. Every drop of ice that melts into the ocean is not only a loss of ice, but also a change in the familiar world we live in. In 2020, according to data from the World Meteorological Organization, sea levels rose by 3 millimeters per year, which is a result of glacier melting and thermal expansion of water. This underscores how the slow but inexorable transformation of polar regions has consequences for the entire world. Rising sea levels are not just an abstract threat, but a real problem affecting millions of people worldwide. As a result of glacier melting and thermal expansion of water, the sea level increases by an average of 3 millimeters per year. According to the National Oceanic and Atmospheric Administration of the United States, since the beginning of the 20th century, the sea level has risen by 25 centimeters, and this figure continues to grow at an accelerating pace. Particularly vulnerable are low-lying coastal areas, such as Bangladesh, where more than 30 million people may face the flooding of their homes by the middle of the century. Island nations like the Maldives and Tuvalu are on the brink of disappearance, as their maximum height above sea level is only a few meters. The problem is exacerbated by the fact that rising sea levels lead to changes in ecosystems, such as saltwater intrusion into freshwater sources, making them unsuitable for drinking and agriculture. Adapting infrastructure to new conditions requires significant investments. For example, in the Netherlands, where a third of the territory lies below sea level, technologies such as flood barriers and water management systems are actively used to protect the population from flooding. These measures require not only financial investments, but also comprehensive planning, including the resettlement of residents from high-risk zones. In some cases, such as in Port-au-Prince, Haiti, local residents are already beginning to migrate to safer areas. By the year 2040, up to 200 million people may become climate refugees if serious measures are not taken to protect coastal cities and islands from flooding. Migration is already observed in regions such as Zanzibar, where local residents are leaving their homes in search of safer living conditions. The adaptation process requires not only technical solutions, but also political will at the government level, as climate change affects not only the economy, but also the social structure of societies. It is important to note that changes are occurring against the backdrop of increasing natural disasters and economic crises, which exacerbate the situation of vulnerable groups of the population. Such challenges require global efforts and cooperation, as no single state can cope with these problems alone. Examples of successful strategies and practices, such as mangrove restoration projects in Bangladesh, show that it is possible to protect coastal areas. Restoring natural ecosystems not only helps in the fight against sea level rise, but also contributes to the preservation of biodiversity. Changes in precipitation patterns due to global warming are one of the most alarming aspects of climate change, leading not only to the intensification of extreme events, but also to an increasing unpredictability of weather conditions. There are numerous studies confirming that, as a result of climate change, various regions of the world are experiencing sharp changes in the distribution of precipitation. For example, in Eastern Africa, where heavy rainfall was traditionally common, there has been an increase in the frequency and intensity of droughts over the past several decades. According to the World Meteorological Organization, in some areas of Kenya, the level of precipitation has decreased by 30% since 2010. This leads to water shortages for agriculture, which is the main source of livelihood for millions of people. Meanwhile, in other regions such as Southeast Asia, the opposite trend is observed. The amount of precipitation is increasing, leading to frequent floods. In Bangladesh, for instance, the number of rainy days has increased by 20% over the past 30 years, resulting in devastating floods and inundations that kill people and destroy infrastructure. These changes require local authorities and farmers to adapt, but traditional methods of farming and urban infrastructure management are becoming less effective. For example, in India, where farmers rely on seasonal rains for planting, changes in precipitation patterns put crop yields at risk. The rural population, dependent on predictable climate, faces risks associated with crop failures, leading to economic losses and population migration. In cities like Mumbai, floods cause overloading of drainage systems, leading to street flooding and the destruction of residential buildings. According to estimates, in 2018, more than 10,000 residential buildings were damaged in Mumbai due to floods, with damage exceeding $100 million. The increase in precipitation intensity and unpredictability also worsens conditions for economic growth in these regions, creating a vicious cycle of poverty and vulnerability. Projections show that by 2030, the number of people at risk from changes in precipitation could increase by 70%. Especially in low-income countries. Such conditions require the development of new approaches to resource and infrastructure management, making the task of adapting to climate change even more complex. The complexity lies in the fact that in most cases, traditional methods such as water storage and the use of drought-resistant varieties are not sufficient to cope with the sharp changes in climate. As a result, the task of adapting to new conditions becomes not only economic, but also social, requiring the involvement of all segments of the population. It is important to note that such changes already require governments and international organizations to review their approaches to planning and development to minimize the impact on the population and the environment. In 2020, the United Nations adopted a program for adapting to climate change, aimed at helping countries address these challenges. But the implementation of such programs remains difficult due to a lack of funding and political will. Ultimately, changes in precipitation patterns already have a significant impact on people's lives, and this trend, according to projections, will only intensify. Geoengineering represents a concept under which humanity seeks to actively interfere with the Earth's climate system to counteract global warming. This idea is based on the assumption that modern technologies can be used to alter climatic conditions to lower the planet's temperature and prevent catastrophic consequences of climate change. The real problem lies in the fact that scientific research shows that inaction would lead to even more severe consequences than the risks of intervention. According to the Intergovernmental Panel on Climate Change, by the year 2030, the planet's temperature may rise by 2 degrees Celsius, causing significant changes in ecosystems and leading to the extinction of numerous species. On the other hand, interference with the climate system presents a complex ethical dilemma, as it may result in unpredictable consequences. For example, changes in one region could affect weather conditions in other parts of the world, leading to droughts or floods. It is important to consider that any intervention requires a thorough assessment of potential risks and benefits. Scientific communities are divided in their opinions. Some believe that geoengineering could become a necessary tool in combating climate change, while others warn about the possible negative consequences that could arise from intervention. According to a survey conducted in 2020 among leading climatologists, more than 50% of respondents supported further research in the field of geoengineering, but with a clear understanding that it should not be the only solution to the problem. There is also concern that an emphasis on geoengineering could distract from the necessary measures to reduce greenhouse gas emissions, which is itself a key element in the fight against global warming. In this context, researchers emphasize the need to develop not only technologies, but also ethical norms regulating the use of geoengineering. Currently, despite promising ideas, there are no technologies that can effectively and safely address the problem of global warming. The questions that scientists are working on concern not only technical aspects, but also social, economic, and ecological consequences. For example, what would be the consequences for countries that might be threatened due to changes caused by geoengineering in another part of the world? Research shows that cooling the planet could have negative consequences for agriculture in tropical regions, which in turn could affect the food security of millions of people. Thus, geoengineering not only presents new scientific challenges to humanity, but also forces a rethinking of existing approaches to shared responsibility for the planet's fate. During discussions at international climate conferences, such as the Paris Summit in 2015, experts raised questions about the legal responsibility for possible negative consequences of geoengineering projects. In this context, it becomes clear that any actions in the field of geoengineering should be carefully considered and justified. Otherwise, humanity risks exacerbating existing problems instead of solving them. For illustration, some scientists point to the need for the creation of international norms and standards regulating the application of geoengineering technologies to avoid climate colonialism, where one country could easily manipulate the climate of another. Taking into account all these factors, it becomes clear that interference with the climate system requires a comprehensive approach and a thorough analysis. The question of how safe and effective such interference can be remains open. Currently, the key aspect is the need to balance the risks of inaction and the risks of active intervention. Sprinkling aerosols in the stratosphere is one of the technologies being considered as a potential solution to the problem of global warming. The idea is to create an effect similar to volcanic eruptions, where particles are released into the atmosphere that can reflect sunlight. Studies have shown that such eruptions, such as the eruption of the Pinatubo volcano in the Philippines in 1991, led to a temporary decrease in global temperatures by 0.5 degrees Celsius over several years. One of the proposed technologies involves the spraying of fine particles of sulfur, which can remain in the stratosphere at heights of 10 to 30 kilometers, creating clouds that reflect sunlight. Special aircraft, such as the Concorde or modified cargo planes, capable of reaching such heights, could be used to deliver these particles to the upper layers of the atmosphere. More exotic solutions, such as the use of high-altitude balloons or even small satellites, which would spray aerosols, are also being considered. However, apart from the potential effectiveness, it is necessary to take into account the side effects. Spraying aerosols can cause changes in precipitation, leading to a decrease in some regions and an increase in others. This could exacerbate water supply problems in arid areas, while in other places there could be an increase in the frequency and intensity of floods. There is also a risk of damaging the ozone layer, as aerosols can interact with atmospheric chemical compounds and accelerate the destruction of ozone. Studies show that even small changes in ozone concentration can have serious consequences for human health and ecosystems. It is important to note that such technologies have not been tested on a large scale, and many aspects remain insufficiently studied. Therefore, additional research is needed to understand all possible consequences of spraying aerosols. Currently, no country has implemented a project to spray aerosols in practice, and most scientists agree that such a practice requires careful evaluation and understanding of the possible risks and benefits. Technologies for capturing and storing carbon represent one of the most ambitious directions in the fight against climate change. Direct capture of carbon dioxide from the atmosphere, often referred to as DAC, direct air capture, has been the subject of active study since the early 2000s. For example, the Swiss company Climeworks launched the first commercial CO2 capture plant in 2018, which can capture up to 1,000 tons of carbon dioxide per year. This process requires significant energy and resource inputs, as its effectiveness depends on the concentration of CO2 in the atmosphere, which is approximately 0.04%. To operate such facilities, infrastructure comparable to the oil industry is needed, but working in the opposite direction, returning carbon to the Earth rather than extracting it. There are several carbon-binding technologies, including mineralization, where CO2 is bound to natural minerals, forming stable carbonate compounds. This process can be observed in the CarbFix project in Iceland, which has been capturing CO2 and converting it into minerals in underground rocks since 2013. In this project, over 8,000 tons of CO2 have been utilized in 3 years. However, such solutions require significant investments in infrastructure for capturing and transporting CO2 to storage sites, making them economically challenging. Long-term carbon storage is also a crucial aspect, ensuring safety over thousands of years. In the United States, for instance, the Geological Sequestration Act of 2009 defines storage sites, such as depleted oil and gas fields. Research shows that carbon can safely be stored in underground reservoirs at depths of over 1,000 meters. However, this requires detailed geological mapping and monitoring to prevent leaks. Ultimately, the scale of investments and technology development needed for carbon capture could reach trillions of dollars, comparable to the total costs of the global oil industry, which was estimated at over $3 trillion in 2020. There are also prospects for using captured CO2 in production, such as in the creation of synthetic fuels or building materials. But these technologies are still in the development stage and require large-scale testing. Research indicates that to achieve a significant reduction in carbon emissions, more than 1 billion tons of CO2 must be captured annually, requiring the creation of a global network of carbon capture and storage technologies. Afforestation and peatland restoration are among the most effective natural solutions for carbon sequestration. According to data from the United Nations Food and Agriculture Organization, restoring 1 hectare of forest can absorb up to 12 tons of carbon per year. Forests not only absorb carbon from the atmosphere, but also serve as homes for more than 80% of terrestrial plant and animal species. Forest restoration also improves soil quality, increasing its fertility and promoting biodiversity conservation. A study conducted in 2020 by researchers from the University of California showed that forests restored on previously logged areas can restore ecological functions and serve as effective carbon sinks within just 10 years. Peatland restoration, on the other hand, has its unique advantages. Peatland ecosystems act as natural filters, cleaning water and retaining nutrients, which prevents eutrophication of water bodies. A study conducted in 2018 found that 1 hectare of restored peatlands can absorb up to 40 tons of carbon per year, while also providing habitats for unique species such as cranes and rare plants. Marine ecosystems, including mangrove forests and seagrasses, also play a crucial role in carbon sequestration. For example, mangrove forests can absorb carbon up to 14 times faster than tropical forests and protect coastlines from erosion and floods. Research shows that mangrove ecosystems can retain up to 80% of the carbon in soils due to their unique root systems that strengthen the soil and prevent erosion. Restoring seagrass meadows also contributes to carbon sequestration and prevents coastal erosion, creating natural barriers against storms and floods. Such ecosystems not only contribute to carbon sequestration, but also increase biodiversity, providing habitats for numerous marine species. For instance, a study conducted in 2019 showed that restoring seagrass meadows in the Caribbean Sea led to a 30% increase in fish populations. These ecosystems provide numerous additional ecological services, such as regulating water flow and preventing soil erosion, making them important not only for combating climate change, but also for sustainable management of natural resources. Ultimately, healthy ecosystems such as forests, peatlands, and seagrasses serve as powerful tools for carbon sequestration, supporting diverse ecological functions and services. Restoring and maintaining these ecosystems can be key steps in combating climate change and preserving biodiversity on the planet. According to the World Wildlife Fund, 80% of the world's forests are affected by human activities, highlighting the need for active restoration efforts. Over the course of millions of years, Earth has been constantly surrounded by objects that pose a significant threat to life on our planet. These objects, known as asteroids and comets, vary in size from small pebbles to massive bodies with diameters of several kilometers. According to NASA, there are more than 30,000 registered objects in Earth's vicinity that cross its orbit. Each of these objects follows its own trajectory, and even small changes in their orbits can lead to potentially catastrophic collisions. For instance, observatories around the world daily track hundreds of such objects, monitoring their movement and assessing potential risks. Astronomers use various methods to determine the orbits of asteroids, including radar and optical observations, to obtain precise data on their sizes and trajectories. These data enable the prediction of potential collisions with Earth and the development of response strategies. Collisions with large asteroids in the past have already occurred and had devastating consequences. For example, about 65 million years ago, an asteroid the size of 10 kilometers struck Earth in the area of the present-day Mexican Gulf, leading to the mass extinction of dinosaurs and significant climate change on the planet. This historical event underscores the need to be vigilant and prepared for potential cosmic threats. Scientific research shows that even objects as small as several dozen meters can cause substantial damage upon entering the atmosphere, generating explosions comparable to nuclear ones. Astronomers are actively studying what are known as celestial dangers, and there is international cooperation aimed at identifying and tracking these objects. For example, the NASA Near-Earth Object Observations Program was established to monitor asteroids approaching Earth with the aim of preventing potential catastrophes. It is important to note that such objects primarily originate from the asteroid belt located between the orbits of Mars and Jupiter, where millions of rocks orbit the Sun. However, some of these asteroids can be ejected from their orbits and directed towards Earth under the influence of gravitational forces. Scientific research in this area continues, and new technologies, such as observations with space telescopes, allow for more accurate determination of the sizes and compositions of objects, which in turn helps predict their potential threat. According to estimates, about 13% of objects crossing Earth's orbit are potentially hazardous asteroids, making their monitoring particularly crucial. Every day, Earth moves through space filled with these potential threats, and it is important for humanity to continue developing technologies for their detection and study to avoid catastrophic consequences in the future. Astronomers continue to make discoveries, and each newly found object can change our understanding of how we can protect our planet from potential asteroid danger. Astronomers around the world use various programs and technologies to detect and catalogue near-Earth objects. One of the most famous telescopes involved in this task is Pan-STARRS, Panoramic Survey Telescope and Rapid Response System, located in Hawaii. Since its launch in 2014, this telescope has discovered more than 30,000 asteroids and comets by systematically scanning the sky and capturing moving objects with high-sensitivity cameras. Additionally, the NEOWISE program, launched in 2009, uses an infrared telescope to search for objects that may be too faint to be seen with visible light. It has already discovered more than 12,000 objects and continues to operate. To enhance detection efficiency, astronomers use algorithms that help process images and identify object movements against static stars. For example, the Moving Object Detection algorithm analyzes sequential images, comparing them to identify changes, which allows for calculating object orbits. Based on these calculations, researchers can assess the potential danger of each discovered asteroid or comet. For instance, if an asteroid approaches Earth within 7 million kilometers, it is classified as potentially hazardous. In this context, international cooperation plays a crucial role. Initiatives such as the International Asteroid Warning Network involve countries exchanging data on discovered objects and jointly developing strategies for their monitoring. This cooperation allows for the use of resources and expertise from different countries, significantly increasing the chances of successful detection and prevention of potential threats. For example, in 2020, within the framework of this cooperation, an operation was conducted to track asteroid 2001 FO32, known as 2001 FO32, which passed by Earth at a distance of 800,000 kilometers, a relatively close distance in astronomical terms. To assess the danger of asteroids, special models such as Sentry, developed by NASA, are used, which monitor potential collisions and provide regular updates on the status of objects. Each newly discovered object is added to the catalogue, and its orbit is recalculated based on new data to ensure maximum accuracy in predictions. Thus, astronomers have a clear picture of which objects may pose a threat and how best to track and study them. It is important to note that even the smallest objects can be dangerous, as demonstrated by the 2018 incident when a small asteroid, only 2 meters in size, entered Earth's atmosphere and exploded over Chelyabinsk, causing an explosion comparable to a nuclear blast. Modern concepts for protecting Earth from asteroid threats are actively developing, and several key methods can be highlighted. One of the most discussed methods is kinetic impactors, which involves sending a spacecraft to collide with an asteroid. For example, in 2020, NASA launched the DART mission, whose goal is to change the orbit of the asteroid Dimorphos by colliding with it in 2022. The principle of operation is that the speed and mass of the spacecraft create enough energy to alter the asteroid's trajectory, thus preventing a potential collision with Earth. Another method is gravitational tractors, which involve using large spacecraft with a powerful gravitational field. These spacecraft should gradually pull the asteroid into a safe orbit using gravitational influence over an extended period. Research shows that this approach requires significant resources and time, but has potential for preventing a catastrophe if the asteroid is detected early. Nuclear explosions are also considered as a means of neutralizing the threat. This concept involves detonating a nuclear device near the asteroid, which would release enormous energy and consequently change its trajectory. Research indicates that with the correct calculation of the explosion's power, the risk of collision with Earth can be significantly reduced. However, this method raises numerous ethical and ecological questions. Nevertheless, all these methods require joint efforts from the international community, as the asteroid threat is a global problem. In 2020, the UN established the Expert Group on Asteroid Monitoring, which brings together scientists from different countries to develop effective protection measures. It is important to note that humanity is transforming from a passive observer of cosmic catastrophes into an active participant in shaping a safe near-Earth environment. This change in mindset demonstrates people's readiness to take responsibility for the planet's future. Technological progress in this area also inspires the development of new technologies, such as laser impact on asteroids, which could become the next step in combating cosmic threats. Scientists from different countries are working on projects aimed at creating powerful lasers capable of altering the trajectory of small celestial bodies. It is important that by the 2030s, many of these technologies may become a reality, providing humanity with tools for protection against potential catastrophes. As a result, the outlook for humanity's future becomes more optimistic, as new protection methods offer hope that we can avoid tragic events like those that occurred in the past. In particular, the study of the Chelyabinsk comet and its impact on Earth serves as a clear example of how important it is to prepare for such threats in advance. The scientific community and states must continue to invest in research and development to ensure that humanity is prepared for any potential threats from space. In recent decades, international cooperation in the field of planetary defense has become increasingly relevant. In this context, numerous initiatives have emerged that unite countries towards a common goal of protecting Earth from potentially hazardous space objects. In the 21st century, in particular, since the creation of NASA's Near-Earth Object Observations program, asteroid and comet tracking has become a crucial part of the global strategy for planetary defense. Over 30 countries are actively involved in monitoring near-Earth objects and exchanging data through platforms such as the International Asteroid Warning Network, IAWN. This network, established in 2015, includes scientists, engineers, and government officials who coordinate their efforts to ensure safe asteroid observation. One of the prominent examples of international cooperation is the AIDA, Asteroid Impact and Deflection Assessment Program, which involves joint missions by NASA and the European Space Agency. In 2021, NASA launched the DART Double Asteroid Redirection Test Mission to test asteroid deflection technology. This mission is coordinated with ESA, which plans to send its Hera mission to study the results of DART. The collaborative efforts of such organizations demonstrate how a cosmic threat can unite countries despite political differences. The importance of data exchange on potentially hazardous objects cannot be overstated. For instance, since the signing of the Tokyo Declaration in 2013, countries worldwide have agreed on principles for data exchange and joint work in case of threats. This document has served as the basis for numerous bilateral and multilateral agreements that facilitate international cooperation in emergency situations. Within such agreements, such as the one between Russia and the United States on joint astronomical observations, scientists can quickly share information about new discoveries. Global threats, such as asteroid impacts, require humanity to overcome political barriers and unite efforts. In 2017, an International Planetary Defense Congress was held, where over 800 specialists from various countries gathered. Discussions on security and joint response to cosmic threats contributed to the development of a unified strategy that includes the creation of backup systems capable of tracking and assessing potential threats. From a scientific perspective, transparency and data accessibility are crucial for all participants. A significant step in this direction was the establishment of the Global Near-Earth Object Information Center, which provides access to information about observed objects for scientists and government institutions worldwide. This enables not only the tracking of dangerous objects, but also the development of effective deflection methods. In the 21st century, the number of discovered asteroids has significantly increased. From 2000 to 2021, over 30,000 near-Earth objects were registered. Thus, the cosmic threat is indeed a factor that unites humanity. Joint missions, data exchange, and observation coordination help create a comprehensive defense system capable of responding to sudden threats. The scientific community and states must continue investing in such initiatives, as demonstrated at the United Nations Conference on Space Research in 2020, where over 100 countries signed a declaration on joint work in planetary defense. Technologies developed within these initiatives may play a key role in ensuring the safety of all Earth's inhabitants in the future. Therefore, the global community must remain vigilant and actively participate in the development of new technologies, such as early warning systems and asteroid deflection methods, to minimize risks associated with potential cosmic threats. Approximately hundreds of millions of years from now, due to the movement of tectonic plates, continents will once again unite into a single supercontinent. Tectonic plates, like giant jigsaw pieces, slowly move across the Earth's surface, shifting at a speed of about 1 to 10 centimeters per year. This movement is driven by convective currents in the planet's mantle, where heated magma rises and sinks, creating continuous motion. As a result of this process, continents currently separated by oceans will begin to approach each other. An example of such an approach is the movement of the Indian plate to the north, which continues to collide with the Eurasian plate, leading to the formation of the Himalayas, whose height in some places exceeds 8,000 meters. There are many theories about how exactly the continents will unite into a supercontinent, but all agree that this process will take tens of millions of years. Scientific research shows that such a unification in the future may occur as a result of several key processes, such as subduction, where one plate descends beneath another, causing the formation of new mountain ranges and changes in the landscape. For example, about 300 million years ago, there was a supercontinent called Pangaea, which began to break apart into the modern continents. The structure of the Earth will change, and oceans like the Atlantic may disappear. while new ones may appear between the newly formed continents. This inevitable movement of plates will also lead to changes in climate, ecosystems, and even the possible emergence of new forms of life. From a geological perspective, Earth is not a static system, but a dynamic and changing one, where each wave, each earthquake, and each volcanic eruption is part of a larger, continuous process. Ultimately, when humanity ceases to exist, these tectonic processes will continue, forming new landscapes and ecosystems. Through tens of millions of years, when some of the current continents will be at the center of a new supercontinent, while others will be submerged, Earth will become completely different, with new mountain ranges and oceans. Studies show that cycles of the formation of supercontinents and their disintegration occur approximately every 300 million years, indicating the constancy of these processes. For example, the plate on which Australia is located is moving northeast, which in the future may potentially lead to a collision with Asia. This process will continue, regardless of the existence of human civilization. Even if we disappear, geological forces will act, forming new continents and oceans. In the end, when we look at our world through millions of years, we will see a landscape that has been fundamentally changed, where tectonic movements will create new contours of the continents. Geologists and tectonic plate specialists suggest that in 250 million years, continents will once again unite into a single landmass known as Ultima Pangaea. This hypothetical model proposes that by that time, continents such as North America, South America, Africa, Europe, and Asia will be gathered into the shape of a vast supercontinent located around the equator. The main movements of the plates responsible for this unification will occur due to the continuous movement of lithospheric plates at speeds up to 10 centimeters per year. Ultima Pangaea is likely to take the form of an irregular polygon with large internal territories and relatively narrow coastal lines. At the center of this supercontinent will be a vast area of land with an extremely continental climate characterized by high temperatures and low humidity. The center of Ultima Pangaea is likely to become a true desert, similar to the modern Sahara or Kalahari, where the average annual temperature may exceed 30 degrees Celsius. Along the coasts, however, the climate will be milder due to the influence of the oceans surrounding the supercontinent. Here, more moderate temperatures and high humidity may create conditions for diverse flora and fauna. Research indicates that such climatic conditions could lead to the formation of unique ecosystems that differ from the present ones. For example, in the southern part of Ultima Pangaea, a vast tropical zone may form, while in the north, conditions may be similar to those in the Arctic. Scientific models also suggest that new mountain systems may arise in this supercontinent as a result of plate collisions, similar to how the Himalayas formed when the Indian plate collided with the Eurasian plate. Therefore, Ultima Pangaea will not only alter the geographical map of the Earth, but also influence climate conditions, the biosphere, and even the migration of animals and plants. It is also suggested that numerous new rivers and lakes may form on this supercontinent, further diversifying the landscape and ecosystems. Research has shown that such changes do not occur in isolation, but are the result of multiple factors, including volcanic activity, changes in ocean levels, and even human activity if it continues. The scientific community is actively discussing these models and their consequences, including the possibility of a new stage in the evolution of living organisms. It is important to note that these models are based on current scientific knowledge, but they may change over time as new discoveries and research in the fields of geology and ecology emerge. In the future, when a supercontinent once again unites the Earth's masses, the climate on this vast landmass will be radically different from the present. Extreme seasonal temperature fluctuations are expected, leading to significant changes in ecosystems. Internal regions of the supercontinent, distant from marine influence, will become true deserts, where summer temperatures can reach 50 degrees Celsius. For instance, in such conditions, extensive zones with arid climates similar to the modern Sahara or Atacama deserts, but much harsher and more barren, may form. Monsoons acting on the coasts will bring abundant rains, creating unique microclimates. These rains can reach 3,000 millimeters per year, fostering lush vegetation in coastal zones where life will be concentrated in limited spaces. The causes of such climate changes will include tectonic processes leading to the formation of high mountain ranges, as well as changes in ocean currents that will affect the distribution of heat across the planet. Internal areas of the supercontinent will experience sharp contrasts between day and night, with temperatures dropping to 0 degrees, creating conditions where complex forms of life will struggle to survive. The biodiversity that remains will be concentrated in narrow coastal ecosystem strips, where marine and freshwater organisms can adapt to conditions different from those on land. These zones will become true oases of life, while vast internal territories will present bleak landscapes where nature will fight for survival. As a result, such conditions will put pressure on species, forcing them to adapt or go extinct. It is expected that in such conditions, primitive organisms capable of surviving in extreme conditions will dominate, while more complex forms of life will lose their positions. Ultimately, the climate of the future supercontinent will be a true arena for survival, where only the most resilient organisms will be able to adapt to harsh conditions. It is predicted that such conditions will begin to develop in several million years, when tectonic processes will lead to the formation of a new supercontinent, which may appear in a period ranging from 100 to 300 million years. In millions of years after the disappearance of humanity, Earth will become a stage for new forms of life that will adapt to changing conditions. It is expected that as a result of climate change and tectonic processes, new ecosystems will emerge that were previously impossible. For example, in conditions of increased temperature and changes in atmospheric composition, organisms that can survive will possess unique adaptations. In oceans where oxygen levels decrease, anaerobic bacteria may develop that can use hydrogen sulfide as a source of energy. As ecosystems transform, on land, plants capable of surviving extreme drought, such as succulents, will appear. These plants will store water in their tissues and adapt to extreme conditions. These new plant species may fill the niches left by the disappearance of familiar forests and meadows, creating entirely new ecosystems that we cannot imagine. Meanwhile, surviving mammals may begin to evolve in different directions, adapting to new conditions. For instance, some may develop nocturnal habits to avoid daytime heat, while others may become more aquatic, developing fins and altering their bodies for efficient movement in water. As a result of this diversity, groups of organisms will occupy ecological niches previously occupied by humans. An example of such a process is the evolution of crocodiles, which, as is believed, have existed for over 200 million years, surviving various climate changes and ecosystems. These reptiles are capable of adapting to the most diverse conditions, and in the future, we may see them transforming into more specialized forms that can hunt both on land and in water. It is important to note that all these changes will occur over millions of years, and it is impossible to predict exactly how life will look in that time. However, known examples from history, such as the extinction of dinosaurs around 66 million years ago, show that new forms of life, often completely unexpected, replace those that have disappeared. Changes in climate and ecosystems will contribute to the emergence of new life forms that can adapt to harsh conditions, ensuring the continuation of life on the planet. Thus, in conditions where dense forests once existed, open savannas with new herbaceous forms of life may arise, competing for resources. Over the course of millennia, organisms will develop completely new mechanisms for reproduction, defense, and food acquisition. For example, new life forms may appear with bioluminescent properties, which will help them attract partners or repel predators. In this world free from humans, life will continue to seek ways to survive, creating complex and diverse ecosystems that can adapt to changes and perhaps even reach new levels of development. Thus, Earth will become a home to wondrous and strange creatures, of which we can only speculate, and their evolution will continue in the infinity of time. Scientists studying evolution are confident that new species will replace the current ones, which will be unlike those we know today. Changes on Earth have been occurring over billions of years, and each moment in human history is but a tiny spark in this vast temporal scale. For instance, around 2.5 billion years ago, during the Archean era, the first simplest forms of life, prokaryotes capable of photosynthesis, emerged. This was a turning point in the biosphere as they began to release oxygen, altering the planet's atmosphere. Over time, approximately 1 billion years later, the oxygen level reached a critical point, leading to the Great Oxygen Catastrophe, during which many anaerobic organisms went extinct. Over the next billions of years, continents continued to shift, forming new geographical landscapes. Plate tectonics, a process that continues to this day, has resulted in the formation of mountain ranges like the Himalayas, which arose from the collision of the Indian and Eurasian plates around 50 million years ago. These changes not only alter the Earth's appearance, but also significantly impact the climate, ecosystems, and, consequently, the life that exists on it. While life on Earth adapts to these changes, internal processes such as volcanic activity continue to shape the planet. For example, volcanic activity on Hawaii has been ongoing for over 1 million years and has created islands that are now home to unique ecosystems and species. Considering that human activity has only been present on the horizon for the last few tens of thousands of years, it is safe to say that our presence is merely a temporary episode in the long history of the planet. Climate changes, caused by both natural processes and human activity, also play a role in the future of Earth. Processes such as orbital fluctuations alter the distribution of solar light, affecting ice ages and interglacial periods. Over the past millions of years, we have observed global temperatures fluctuating, leading to the shift of ecosystems and the extinction of entire species. As humanity continues to develop, internal processes of the planet, such as erosion, sedimentary processes, and mountain building, continue to slowly but inevitably change the landscape. Ultimately, in the distant future, when life on Earth takes on new forms, the planet may become entirely different. Such a planet where the mountains we know today will be erased, and oceans will occupy new spaces, washing away old shores. According to geologists' estimates, in the future, through millions of years, the level of oceans could rise by tens of meters, altering the contours of the continents. The nearest oceanic depressions and reefs will continue to be affected by waves and currents, forming new ecosystems, possibly even unique forms of life that we cannot currently imagine. The Earth's crust will continue to cool, while internal processes such as radioactive decay will gradually decrease the heat, and eventually, the planet may become colder and less active. At this time, when other forms of life adapt to new conditions, humanity may become merely an artifact from a past epoch, similar to dinosaurs that went extinct millions of years ago, leaving behind only fossils. Astronomical and geological processes continue to act on the planet, and eventually, Earth may become unrecognizable. With each million years, new forms of life will emerge, adapting to changing conditions, while old species will disappear. Scientific research shows that with each new generation, evolution creates ever more complex ecosystems that will continue to develop and adapt. As a result, under the influence of internal dynamics and external factors, Earth will continue its long history of change, where human presence is but a fleeting moment in eternity. Ultimately, the planet we live on is a dynamic system, constantly in motion, and its future will be as unpredictable as its past. Earth may become a home to entirely new forms of life that will exist in conditions we can only conjecture. The Sun, as a main sequence star, gradually increases its luminosity, which has direct consequences for Earth and its inhabitants. Currently, the Sun's luminosity is increasing by about 8% every billion years. This process is linked to changes in thermonuclear reactions in the star's core, where hydrogen is converted into helium. In about 1 billion years, the Sun's luminosity will increase by 2%, leading to a significant rise in Earth's temperature. Scientific research indicates that in 300 million years, oceans will begin to evaporate, creating conditions unsuitable for the existence of complex life forms. In this scenario, the surface temperature on Earth could reach values exceeding 100 degrees Celsius. The increasing amount of solar radiation will contribute to processes that lead to the disappearance of tropical forests and Arctic ecosystems. The biosphere, as a result of this change, will gradually retreat to the poles, where conditions will be more suitable for life. For example, new ecosystems may arise in the Arctic, but they will be significantly different from those we know today. It is expected that by 500 million years, as a result of these changes, only simple life forms, such as microbes, will remain on Earth. Specialists predict that by this time, the atmosphere will have changed significantly, and the level of carbon dioxide will increase, leading to a greenhouse effect. Specialized models show that as the temperature rises, oceans will lose oxygen, making life in them practically impossible. Ultimately, in 1 billion years, when solar activity becomes significantly higher, the temperature on Earth could become so high that the planet will turn into a desert where water will be absent and landscapes will resemble modern-day Martian ones. Such changes in solar activity and their impact on the biosphere require careful study, as they can provide us with a key to understanding the future of our planet and life on it. The existence of complex life forms, as we know them, depends on the stability of the climate and conditions that are becoming increasingly fragile in the face of increasing solar luminosity. By the time solar energy becomes too intense, there may already be completely different life forms on the planet, adapted to extreme conditions that we cannot even imagine. It is important to note that such changes will not occur suddenly, but will take millions of years, giving humanity time for adaptation and possible search for new places to live. As the planet cools over vast periods in the distant future, the active tectonic movement of plates will gradually subside. This process will take millions of years, when the internal heat of the Earth becomes insufficient to maintain convective flows in the mantle. Currently, the temperature at the Earth's core reaches approximately 4,000 degrees Celsius, but in the future, as this resource is depleted, the mantle will begin to lose its mobility. The convective flows that currently move tectonic plates will slow down and eventually cease. This will result in the disappearance of active volcanoes and earthquakes, which once shaped the planet's landscape. Continents will remain stationary, leading to a significant flattening of the landscape. Erosion caused by atmospheric phenomena will gradually smooth out mountain ranges, breaking them into smaller sections and transforming them into plains. For example, mountain systems like the Himalayas, which continue to grow due to the collision of the Indian and Eurasian plates, will eventually be mere remnants of their former activity. Ultimately, billions of years later, only flat plains will remain where once towered majestic mountains. Since tectonic processes will no longer replenish minerals and nutrients, the cycle of elements, crucial for life, will be disrupted. This will lead to the depletion of necessary resources for complex forms of life. In such conditions, ecosystems will begin to degrade, and biological diversity will wane. Existing organisms will have to adapt to new conditions or go extinct, as has happened in Earth's history when mass extinctions altered the planet's biosphere. In the end, the planet will become geologically dead, with life, if any remains, existing only in isolated ecosystems. It is expected that by this time, the atmosphere will have significantly changed, as the absence of volcanic activity will lead to a decrease in carbon dioxide levels and a depletion of oxygen, resulting in catastrophic consequences for the remaining species. Scientific research indicates that when the Sun reaches the red giant stage in about 5 billion years, the planet may not be able to withstand the changes in solar activity and will be engulfed in its core. In 5 to 7 billion years, the Sun will begin to transform into a red giant, a process triggered by the exhaustion of hydrogen in its core. Currently, the Sun is burning hydrogen through thermonuclear fusion, but as its reserves dwindle, the star will behave like an aging organism, losing its strength. As a result, the core will start to contract under the force of gravity, while the outer layers will begin to expand. This expansion will cause the Sun to grow in size to the point where it will engulf the inner planets, including Mercury and possibly Venus. Scientists suggest that even Earth may fall within the expanding Sun if it isn't destroyed beforehand by other processes. At this time, the temperature on the planet will rise to several thousand degrees Celsius, leading to the evaporation of oceans and the atmosphere. Scientific models indicate that just 1 billion years after the start of this process, the surface temperature on Earth will reach a point where all life will be destroyed, and the oceans will turn into steam. When the Sun becomes a red giant, its diameter will be approximately 1 astronomical unit, 800 times larger than its current size, and it will fill a significant portion of the sky, appearing as a massive glowing disk. This spectacle will mark the end of our planet's existence, with a scorching surface illuminated by bright light and a sky painted in red and orange hues. The Sun will appear as a colossal star that completely engulfs the inner solar system. Ultimately, as all inner planets are consumed, the Sun will shed its outer layers, creating a planetary nebula and leaving behind only its core, which will become a white dwarf. This core will be roughly half the size of Earth, but with a mass comparable to the Sun's. Solar winds and radiation emitted at this stage will create an incredibly bright and powerful phenomenon that can be observed from vast distances in the cosmos. The geological heritage of Earth is a vast book with pages that preserve information about billions of years of our planet's evolution. Each geological formation, each layered structure in rocks, is a record of events that occurred in the past. For instance, sedimentary rocks form from particles that settle at the bottom of oceans and rivers, and can preserve traces of life, including fossils that provide insight into the organisms that inhabited these areas millions of years ago. Volcanic rocks like basalt are evidence of powerful eruptions that altered landscapes and atmosphere, while metamorphic rocks tell of processes that occurred deep within the Earth's crust, where temperature and pressure changed the composition and structure of existing rocks. These processes have been happening for billions of years, starting with the formation of Earth around 4.5 billion years ago. Layers formed during different geological epochs can be studied by scientists such as geologists and paleontologists, who use radiometric dating methods to determine the age of these formations. For example, carbon dating can determine the age of fossils, while methods based on uranium decay help establish the age of ancient igneous rocks. Earth has various geological epochs, such as the Archean, Proterozoic, Paleozoic, Mesozoic, and Cenozoic, each of which has left its mark on the geological record. In the Archean era, about 3.5 billion years ago, the first single-celled organisms appeared. And in the Mesozoic, which lasted from 250 to 65 million years ago, dinosaurs dominated. These epochs are preserved in geological layers that can be read like the pages of a book. For example, fossilized dinosaur remains found in sedimentary rocks indicate that they inhabited Earth for millions of years, allowing us to study their anatomy and behavior. Understanding the geological heritage also involves comprehending catastrophes such as mass extinctions, which have left their marks in geological layers. One of the most famous is the mass extinction at the end of the Mesozoic, which occurred around 65 million years ago and is linked to the impact of an asteroid that changed the climate and ecosystems on the planet. These events not only altered the course of evolution, but also left clear traces in sedimentary layers that can be identified through the analysis of chemical composition and fossils. The geological heritage of Earth is not just a collection of stones and minerals, but a true chronicle that helps us understand how life developed and what changes occurred on the planet throughout its long history. Each layer of rock can contain information about climate, sea level, and biological diversity in different epochs. Geologists can use data on tectonic plates to reconstruct the former continents and oceans that existed in the geological past. This allows for a more complete understanding of how Earth looked at different historical moments. Geological maps created by scientists can show how the boundaries of continents changed and how mountain ranges were formed. For example, the collision of the Indian and Eurasian plates led to the formation of the Himalayas, which occurred around 30 million years ago. These facts become visible through the study of geological structures and processes that have been occurring for millions of years. Each rock, each fossilized form of life, serves as an important clue for scientists who strive to decipher the history of Earth and understand how it may change in the future. Studying ancient catastrophes requires scientists to use various methods that enable them to gather information about events that occurred millions and billions of years ago. One of the key tools in this field is the analysis of isotopes. Isotopes of elements such as carbon, oxygen, and sulfur help to understand climate changes and ecosystem fluctuations. For example, analysis of carbon isotopes obtained from fossils allows scientists to determine how the level of carbon dioxide has changed over millions of years and how this has affected life on Earth. Scientists like Dr. Emily Bennett from the University of Cambridge study isotopic ratios to reconstruct ancient climate conditions and identify the relationship between climate and mass extinctions. Paleontological data also play a significant role in understanding catastrophes. Fossils found in various layers of the Earth provide insights into which species existed at specific historical moments. For instance, the discovery of dinosaur fossils in a layer dated to approximately 66 million years ago confirms the theory of a catastrophe that led to their extinction. Research conducted by a group of paleontologists led by Dr. John Hopkins demonstrated that there was a sudden change in ecosystems around this time, likely caused by a meteorite impact. Geophysical research also provides important data on catastrophes. Seismic sounding methods allow scientists to study the internal structure of the Earth, identifying layers that may indicate volcanic activity or earthquakes. For example, using high-precision seismic data collected in the region of the Pacific Ring of Fire, researchers were able to establish that large volcanic eruptions occurred every 300,000 years, which is linked to an increase in the frequency of earthquakes in this region. Modern technologies such as computer modeling and satellite technology enable scientists to look deeper into the past of the planet. With the help of satellite images, it is possible to track changes in the landscape caused by natural disasters such as floods or landslides. For example, data collected by NASA satellites helped researchers understand how climate change affects the Greenland ice sheet, which could lead to a rise in sea level. All these methods, used in a comprehensive approach, allows scientists to create detailed pictures of ancient catastrophes and their consequences for life on Earth. Modern research conducted by a group of geologists led by Professor Mark Taylor has shown that some of the largest catastrophes, such as the Permian extinction, were likely caused by a combination of volcanic activity and climate changes, which is confirmed by geochemical analyses and paleontological findings. Studying geological catastrophes plays a critically important role in understanding contemporary processes and predicting future events. Scientific research conducted by scientists such as Dr. Emily Winters from the University of California, Berkeley, demonstrates that studying ancient catastrophes, such as meteorite impacts and volcanic eruptions, can help in forecasting future natural disasters. For example, analyzing samples from the Chicxulub crater in Mexico, where a meteorite impact caused the mass extinction of dinosaurs around 66 million years ago, allows scientists to understand how such events affect planetary climate conditions. The work of an international group of geologists, including researchers from Mexico, the United States, and Europe, has collected data on the distribution of stratigraphic layers, which show how life on Earth adapted and recovered after catastrophes. These data are crucial for creating models that help predict the consequences of contemporary climate changes caused by human activity. For instance, in 2020, a group of scientists from the University of Liverpool presented results showing that sea levels could rise by 1 to 2 meters by 2230 due to the melting of glaciers, leading to the flooding of coastal cities. One of the key aspects of studying geological catastrophes is understanding the temporal and spatial scales at which they occur. For example, the eruption of the Toba volcano in Indonesia around 77,000 years ago caused a global winter that lasted for several years and led to a significant reduction in human population. This event was a catalyst for rapid evolutionary processes, as confirmed by genetic studies conducted in 2016 by researchers from the University of Cambridge. It is important to note that studying these catastrophes not only shows the vulnerability of human civilization to natural forces, but also teaches us humility and readiness for unpredictable changes. Research conducted in 2018 showed that cities located in high-risk zones can use data from past catastrophes to develop effective adaptation strategies, such as building protective structures and improving emergency response systems. For example, New York City, as part of its strategy to combat flooding, invests billions of dollars in projects such as creating drainage systems and protective dams based on data from past hurricane impacts. These measures can significantly reduce damage in case of future catastrophes. Understanding the history of Earth and its catastrophic events provides us with tools for adapting to changes in our environment. Forecasts based on historical data allow us not only to prepare for possible threats, but also to develop sustainable practices that help preserve ecosystems. For example, the restoration of ecosystems in areas affected by catastrophes requires a deep understanding of the dynamics of natural processes. Research conducted in 2020 in Australia showed that the restoration of coral reefs after mass extinctions is possible only under the condition of preserving natural conditions. Thus, studying geological catastrophes becomes important not only for historians and geologists, but for all of us, as it shapes our understanding of the future based on knowledge of the past. Each new fact obtained from research opens new horizons for understanding complex processes occurring on our planet. Statistics show that, according to UN estimates, by 2230, around 100 million people may become victims of climate catastrophes if immediate measures are not taken. Geological catastrophes, such as volcanic eruptions, earthquakes and floods, not only shape our planet, but also serve as a mirror reflecting the fragility of human life and humanity's place in the universe. Understanding that such catastrophes are an integral part of Earth's history forces us to view evolution from a new perspective. For instance, approximately 65 million years ago, a mass extinction caused by an asteroid impact led to the disappearance of over 75% of all species on the planet, including dinosaurs. This event not only altered ecosystems, but also paved the way for the emergence of mammals, including humans. Thus, catastrophes act as catalysts for evolutionary changes, underscoring that life on Earth is constantly on the brink of extinction. The progress we perceive as linear and predictable is, in reality, the result of random and unpredictable events. Scientific research shows that each major catastrophe creates new ecological niches, where only the most adaptable species survive. This is confirmed by the work of paleontologists like Dr. Dave Polly, who studied fossils and found that after each mass extinction, new species with unique adaptations emerge, highlighting the constant change in life on Earth. Awareness of the catastrophic element in our history undermines illusions of stability and progress, making us question the randomness of our existence. We cannot ignore the fact that our civilization stands on a fragile foundation created by millions of years of geological processes. For example, a study conducted in 2009 by a group of scientists from the University of California, Los Angeles, showed that there is an 80% chance of significant earthquakes in California within the next 30 years, emphasizing the need for preparedness for unexpected events. In our quest to control nature, humans often forget their limitations. Scientific achievements, such as the construction of earthquake-resistant buildings, give us the illusion of control. But even the most advanced technologies cannot guarantee safety from the power of nature. This realization raises philosophical questions about the meaning of life and our place in the world. As a species, we are in constant interaction with our environment, and any of our actions can have unforeseen consequences. This applies not only to ecology, but also to social structures. Historical examples, such as the fall of the Roman Empire, are often linked to natural catastrophes that affected the economy and social structures. Ultimately, understanding the fragility of our lives in the face of catastrophic natural forces underscores the need for humility and responsibility, both to ourselves and to future generations. Each new catastrophe, whether local or global, reminds us that life on Earth is more than just a struggle for survival. It is a complex and multifaceted process where chance and necessity go hand in hand. For example, in 1986, a magnitude 8.2 earthquake in Mexico killed over 10,000 people and demonstrated the vulnerability of cities built by humans. Such events not only cause physical destruction, but also require us to rethink our place in the world, prompting us to ask, what does it mean to be human in such a chaotic and unpredictable environment? The study of Earth's history demonstrates that disasters, despite their destructive nature, often serve as catalysts for evolutionary changes and the emergence of new forms of life. For instance, the mass extinction that occurred around 66 million years ago at the end of the Cretaceous period wiped out about 75% of all species, including dinosaurs. However, this event paved the way for mammals, which were able to occupy ecological niches left vacant by the disappearance of these large reptiles. Over the course of tens of millions of years, mammals evolved, leading to the emergence of such forms of life as humans. The destruction of old ecosystems and species creates space for new evolutionary experiments. For example, after volcanic activity that formed large craters like the Toba crater in Indonesia, significant climate changes occurred, which in turn altered ecosystems and allowed new species to adapt and develop. In contrast, more recent events, such as the meteorite impact that created the Chicxulub crater in Mexico, also contributed to the turnover of biological communities. It is known that after this event, only those species that possessed certain adaptive characteristics survived, which gave rise to new species, including mammals. In this context, disasters can be seen as important moments in Earth's history, when chaos and destruction became the basis for a new order and development. The processes of transforming the planet are continuous and cyclical, where each end becomes a beginning of something new. In this context, it is worth remembering that over billions of years, Earth has experienced numerous disasters, each of which led to significant changes in the biosphere. For example, at the end of the Permian period, around 250 million years ago, the most catastrophic event in Earth's history occurred, wiping out 93% of all marine species and 71% of terrestrial species. However, this led to the appearance of new species in the Triassic period, such as the first dinosaurs and mammals. This continuous cycle of destruction and renewal is recorded in the geological record, where we see how new ecosystems and biological communities were formed as a result of disasters. Earth is not just a planet, it is a living entity, constantly changing and adapting to conditions. In every new layer of rock, traces of the past are hidden, and every crack in the earth tells a story of how life overcame difficulties and found ways to survive. Our planet, like life on it, is an endless process in which every end becomes a beginning of something new. As we conclude our journey through Earth's history, I wish you a peaceful night and invite you to continue contemplating the magnificent history of our home in the universe, even in your dreams, where images of ancient catastrophes and rebirths can blend with your own dreams, creating new and wondrous worlds. Remember that each moment, each breath on this planet is part of an unending cycle of life.